Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on inside as we jump into section 6.4 in the Big Ideas Math Integrated Math 3 textbook. We are now adding and subtracting rational expressions. We just came off multiplying and dividing, and adding and subtracting is a whole nother wrinkle, especially when it comes to needing a common denominator. So factoring is still involved, and finding that least common multiple is something that we're going to be prepping for, I'm sure, to begin with, before we even do the common denominator stuff. I will start with common denominators, and then we'll start with uncommon denominators, I suppose. We'll get into everything under the sun there. 58 questions in total. Jump to the description section down below to find the PDF of said textbook section and all the problem set, and we're going to begin with the lecture portion. If you want to find problem number 1 or problem number 3 or whatever you want to start with in the problem set, go to the description section down below and find that in the timestamp. I'm going to start with the lecture. Let's start rambling. We are going to add or subtract rational expressions, rewrite rational functions, I don't know what that has to do with yet, and simplify complex fractions. I think a complex fraction is like a fraction within a fraction. So like a over b divided by c over d, kind of like that. So yeah, complex fractions is going to be the new phrase here. Reciprocal, I suppose, is still used in some capacity. We'll see when. Now, as with numerical fractions, the procedure used to add or subtract two rational expressions depends on whether the expressions have like or unlike denominators. I said common or uncommon, but that still works. To add or subtract with like denominators, simply add or subtract their numerators. Place it over the common denominator. So this c don't change right here, and it compares just like that. And I don't want to speak too big on fractions, but I'm just going to do it with numbers. You know, if I do 2/5 plus 1/5, that's 3/5, right? It's not 3/10. Okay. For example, if I did 2 plus 1, that's 3, right? How come? Well, it's 2 over 1 plus 1 over 1 equals 3 over 1. I mean, it's a common denominator thing that we do. So as long as we have the same thing that we're comparing, we can add the top appropriately. So a and b add together, and in some cases they will combine if they're like terms. Same thing with subtraction. So addition and subtraction have the same rules under the sun for those things. Whereas when we multiply straight across. That bottom multiplies with that other bottom. So just don't forget that aspect of it. A couple quick examples of these. 7 over 4x plus 3 over 4x becomes 10 over 4x, but that can also reduce. 10 over 4, you can divide each by 2 and get 5 over 2x as a whole. So when separate, we didn't have anything to reduce, but when together, there was something to actually simplify. And that's something that can happen with our polynomials as well, by the way. We can combine like terms to something on top, and you're going to see us do that. We can combine like terms to something on top that can then be factorable and can then maybe cancel with something on bottom. Now with the subtraction in the same way, 2x minus 5 becomes exactly that. Same like denominator, but nothing could simplify here. Maybe if this was plus 12, then you could factor a 2 out and the x plus 6 is canceled, but that's not the case here. To add or subtract two rational expressions with unlike denominators, you find a common denominator. Rewrite each rational expression using the common denominator, then add or subtract. So what we see in this scenario here is this one divides by c and this one divides by d. You want to multiply top and bottom here by d and this top and bottom here by c. At least if you don't know a least common multiple, find some common multiple, and c times d can be exactly that common multiple here. But you got to multiply top and bottom the same. I don't think I need to explain something that you know about how this works and why this works. But the idea behind this for us is we're going to multiply factored quantities that are missing from the other fraction, from the other denominator, and we're going to make that common. So you're going to see that with polynomial examples, obviously, in just a moment. Subtraction is very much the same, and they show it as combined as one fraction. When we're simplified in the end, guys, our simplification partially means get it as one fraction. So that's our goal. To find the least common multiple of two or more expressions, factor the expressions completely, because the least common multiple is the product of the highest power of each factor that appears in any of the expressions. They said that phrasing a lot better than I ever could, and I'm sure I couldn't repeat it in that exact same way, but they're right. If I had the numbers 4 and 6, what's the least common multiple of the numbers 4 and 6? Because it ain't 24. You see, 4 is 2 times 2, and 6 is 2 times 3. Each of them share a factor of 2, but this is missing a 3, and this is missing another 2, right? So if I multiplied this by 3 to get 12 and by 2 to get 12, you'd find out the least common multiple is 12, not 24. You don't have to multiply by 6 and by 4 when there's something smaller. That's especially going to be the case for these bigger polynomial expressions. says find the least common multiple of 4x squared minus 16 and 6x squared minus 24x plus 24. Well, if we factor this out, if we factor a 4 out here, and then you factor this difference of two squares, and here you get a GCF of 6, and you factor this into x minus 2 quantity squared, you can see what's missing in the other terms. I'm not going to turn 4 into 2 squared or anything like that. I'm just going to leave it like a 4. 4 and 6 have a GCF, or well, it's the same thing I just mentioned. They each share a 2, but then one of them's missing a 3 and one of them's missing another 2. So the least common multiples, you got to find everything and join them all up together for what's missing in the other guy. For example, this one is missing that 3 I was bringing up, and it's missing another x minus 2. So we got to square that thing, and this thing is missing another 2, and this thing's missing an x plus 2. So when we end up multiplying them, this just asks for the least common multiple. When we do common denominator set, we're going to multiply what's missing in each of these. But this is the answer for either one. This is missing that 2 squared. 2 times 2 is 4 times 3 is 12. Boom. And then the x plus 2 would go here, and the x minus 2 squared goes there. Give me one sec. I got a nose itchy issue. Okay. Did I call it a nose itchy issue? Okay. Anyway, so you find what's missing in the other thing. So because what else would you do alternatively? You'd multiply this whole thing by 6x squared minus 24x plus 24, and you'd multiply this whole thing by 4x squared minus 16. That is way too much to do. Way too much to do. Plus, it's not the least common multiple. It's just a common multiple. So they're getting you prepped to use the common denominator practice with fractions without doing it first. So I assume that's what we're going to do in our problem set. I don't know, but that's the assumption. So example 3, now we're going to find this sum. That means do a simplification of this. They say use the definition for adding rational expressions with unlike denominators, where they are, that's interesting. They're doing exactly opposite of, oh, there are two methods. Okay. So method 1, I'll tell you what, guys, I don't plan on using method 1. Method 1 says multiply top and bottom of this quantity. Multiply top and bottom of that by over there, and multiply 9x squared to top and bottom over here. So, and then you have, boom, a common denominator. The thing is, though, there's probably some sort of common factor on top and bottom that can then cancel that we would have noted to begin with, which is a 3x apparently. So I don't know. It turns into what you see. I'm not going to bother myself too much with method 1. I want to speak more on method 2. We just came off least common multiples, so here I want to find a least common denominator. That's what LCD stands for, not liquid crystal display, but least common denominator. Find the least common denominator and then add. So this is what I would do. I would attempt to find common factors in your terms and things like that. Factor them as much as possible and find what's missing in the other fraction. So when you factor a 3x out of here, I'm dealing with denominators first. You actually don't want to factor anything up top right now. You don't, because we're going to want to combine like terms wherever we can. But factor the bottom, 3x times x plus 1. Notice that this 9x squared is totally missing an x plus 1 factor. So if I multiply this by x plus 1 on top and bottom, and this one is missing a whole other 3x factor. You see 3x times 3x is 9x squared. So this will get them a common denominator, but with less factors involved. Notice how this had 9x squared times 3x plus 1 times an additional 3x that really just isn't needed, and you find out that it ultimately, eradicates itself. They cancel out here on top and bottom because, well, it was an extra set that wasn't needed. It's like if I turned, again, this thing into 24, and then you have to reduce it by dividing it by 2 to get it back down to 12. So it's the same thing here. This is the methodology I'm going to work with. Find out what's missing in the other guy factor-wise and multiply top and bottom by it. So you're getting least. Now what happens on top is 7 distributes with x plus 1. X multiplies with 3x, and you get these two things here. And then I'm not saying combine like terms because nothing combines, but they bring it all as one fraction. They write it as one fraction, nothing combined, and at this stage, nothing actually factors either. So we're done with it there. I'm a method 2 guy. I'm not going to be doing method 1, unless they force it and say, which method do you prefer? Explain your reasoning. Subtracting, listen, it's the same as adding when it comes to common denominators, all that. The only one trick is the distribution of the negative, and we'll get to that. So first thing they do is what I would do. You factor 2x minus 2 into 2 times x minus 1. You factor this into this guy here. Notice they both share an x minus 1, so that's not missing in either set, but this is missing a couple 2's, and this is missing a couple x minus 3's. Now you can see that appear right here. I tend to write parentheses around it, but it's cool. So that means that, the thing you have to do here is you do have to distribute. That means FOIL. So x plus 2 times x minus 3 becomes this guy. And then negative 2x minus 1 multiplies with 2 here. A lot of negatives involved, and we are going to subtract in a moment. That's what I have to talk about. So, and then on bottom, you have this times that as one common denominator set. So you can move them all in as one single fraction right here. So this minus this. Now notice, I didn't need parentheses here. I just needed to show you that it's this guy minus that guy. Notice you are subtracting this set. A common thing that students do is they only subtract the first term without parentheses. You won't notice it. That's maybe a reason why I wrote it here. But with parentheses there, you start to distribute that negative into there. It needs to apply to both terms. So instead of just subtracting negative 4x to turn to plus 4x, this is also minus negative 2, which is plus 2. So when you combine like terms, oh, it shows it right here. When subtracting, remember to distribute the negative. Common error. They're not wrong. This is a very common error for students for subtraction. And that's one difference between subtraction and addition. Otherwise, they have the same kind of problem. Now, they do one extra thing, and I hope that there are a lot of problems like this. It almost validates for you that you're doing something right. Look, we're going to combine like terms up top, and then we have this. Don't distribute the bottom, but you want the top to not have been factored ever yet beforehand, so you can combine like terms, because now this is factorable. This factors into this guy, and guess what? It just so happens that something also cancels on top and bottom, which is the ultimate validating feeling that you're cleaning something else up. And like I think I said at the end of the last video, I love to make problems that do this. It's hard to do. It's hard to make problems like this, but I love to make problems that clean up in such a way that have something that cancel thereafter. Now, of course, just like the section 6.3, they are including this as a restriction. I will still follow what they do. I'm going to stop griping about it, but they are only showing restrictions for things that cancel, not things that still exist. For example, x can't equal 3, but they don't mention it because we can tell. We can't tell here that x can't equal negative 1 because those actually it shouldn't be negative 1. That's a mistake on their part. That's a x minus 1, right? That should be a positive 1. So, okay, so they have a little mistake. But, okay, anyway, in addressing the mistake, you wouldn't know that x can't equal 1 because that part's completely gone from this thing. What we want to state again is that this original expression is equivalent to this expression in every which way, including the fact that if x isn't allowed to equal 1 here, because if x equals 1 here, you get 0 in the denominator. So x can't equal 1 here. X, of course, can't equal 3, but we can still tell. And I'm going to stop griping about that. But x can't equal 1. That is a 1. That's a mistake on their end. Unless I missed something, and I don't think I did. Okay, rewriting rational functions. Now, I don't know what this is about yet. Rewriting a rational function may reveal properties of the function and its graph. In example 4 of section 6.2 used long division. Yes, we did. Also synthetic division. In the next example, we will use inspection. Okay. Oh, so we're going to graph again. I hope this isn't a big part of this section. This isn't ever a way that I would do a kind of problem like this. I can see a reason to talk about this, though. Okay, let's go into it. Example, rewriting and graphing a rational function without the division version, even though it's a fraction. Rewrite this in this form, graph the function, describe the graph of g as a transformation. So we're doing the things we did in 6.2. We're even graphing again. I'm going to go very fast on the graphs, guys. It's my feeling that we covered 6.2, so we'll do the graph part. But what we're doing differently is we're not doing division on this divided by this to write the result. We're using inspection. I didn't use that. I haven't ever thought of that phrase as a math phrase. I don't know if that's a real one, but it works. They're doing something from within to split it up. They're x plus 1 is some denominator, but if I split up this numerator into two different, let's make x plus 1 a common denominator of two different fractions, like what they're showing right here. It's split up. I know it crosses out here. We'll talk about that. But let's rewrite it. We're splitting our denominator. We'll make it common among two fractions, but we're doing it so that one of them divides with x plus 1. That's their version of inspection. I guess it takes a moment to feel out what it is that they're doing, but they're saying, let's get a common x plus 1 factor among what we have here. X plus 1 is not a common factor of this unless I make 3 one of the common factors, apparently. So split up 5 into 3 plus 2, because I want 3x plus 3 to turn into 3 times x plus 1. So when I split them up, the x plus 1s divide. And when they divide, then you have an integer, a quotient, if you will, and then a plus 2 over x plus 1. This is like a quotient and a remainder, sure. We never divided, in the way that we do longer synthetic division. and we rewrite it in this form so that we do its graph. I'm not going to get deep into the graph, but your vertical asymptote is x equals -1, horizontal asymptote is y equals 3, and that's revealed through here. Your 2 is 2 divided by 1, 2 divided by 2, 2 divided by 4, things like that. We did a lot of those, and we're going to do some more of those. It's translated 1 unit left, 3 units up from the graph of f of x equals 2 over x. Okay. Any word problems? Not yet. Complex fractions. A complex fraction is a fraction that, yes, contains a fraction in its numerator or denominator. So when I say fraction within a fraction, there it is. Like this right here. Oh my goodness. A complex fraction can be simplified using either of the methods below. I tend to use only one method, so let's figure out which one they say. If necessary, simplify the numerator and denominator by writing each as a single fraction, then divide by multiplying the numerator by the reciprocal. That's what I do. I do method number 1. I don't know what method number 2 is yet. Let's see. Multiply the numerator and denominator by the LCD of every fraction. I don't do that. We'll look at the 2 examples and we'll see. By the way, going back again to the other previous 2 methods, did I use method 1 or 2? I use method 2. So I use method number 2 of finding the least common denominator, least common multiple of the denominators here, as opposed to just multiplying straight up what the other denominator shows. So I use method 2 for this, and then I use method 1. The method numbers don't matter. I'm just talking about the methods themselves. And I use method 1 here. So in method number 1, they say simplify this complex fraction. What they do is they first, this fraction's good and taken care of. This is just this over that. And then we're going to divide this other one. So we're actually doing division here as well. What's really interesting, 6-4, guys, it covers multiplication with common denominators. It covers division here with complex fractions. We'll get into that in a moment. And then it also covers graphing. So it covers every section that we've done before. It doesn't cover inverse variation, I guess, not yet. But it covers 6-2 and 6-3 as well. So this is a pretty big section. This might be a while. Anyway, it's the denominator. It's this bottom set here that's not yet cleaned up. If I want to do this divided by this, it would be really, really helpful if this was rewritten as one single fraction. So in order to do that, we want to find a common denominator. Looks like they go very fast in their work, but we multiply this top and bottom by x plus 4. It becomes 2x plus 8. And we multiply this top and bottom by x. I don't know if I can write all this and fit it all. But this is x over x. This is x plus 4 over x plus 4. So on bottom, we get x plus 2x plus 8 all over x times x plus 4. And now x plus 2x is 3x. This is where you get your 3x plus 8 over x times x plus 4. Now that you have this, and they didn't really rewrite this next step, and I probably will each time, I would rewrite it as division like this afterwards, so you know what you're doing in your flippage, and you don't make a mistake. Often people do. But this division becomes multiplication by the reciprocal. Right, so there's the division, boom, multiplication by the reciprocal. This is my preferred method. This is my method of choice. And then, you cancel things out, whatever. I would cancel out the x plus 4s, and I think that's it. 5 times x over 3x plus 8, boom, you get there. And they list restricted values. X can't equal -4 because it's one of the canceled sets. Why can't x equal 0 when it's up top? Because it wasn't always up top. It was, at one point, down on bottom. It was down on bottom right here. And, yeah, that's it. Okay, and then the implied one, 3x plus 8, right? It's implied. It's already in the denominator. Method 2, I'm not going to deal with too much here, but they're looking at everything, finding the least common denominator of both sets, multiplying by it to clear them out beforehand and write as a single fraction. I'm just not going to get into it. It's not what I'm going to do. Listen, look at it, observe it, like it. I don't know. It's not my way of going about it. The thing I also like about method number 1, and I just mentioned it, is this goes back to what we did in section 6.3. This literally is one of the things we did in section 6.3. This doesn't really take on that 6.3 appearance anymore. Okay, that's the end of the lecture portion. They didn't cover word problems. That's not to say they won't give us word problems, but they didn't cover any in the lecture. Let's do the vocabulary and core concept check. We have numbers 1 and 2. Complete the sentence on number 1. A fraction that contains a fraction in its numerator or denominator. It's called a complex fraction. We just saw that phrase. So we're bringing it back. And number 2 says, explain how adding and subtracting rational expressions is similar to adding and subtracting numerical fractions. Well, when you have a common denominator, you can add them together. Keep the denominator and add the numerators. and simplify if necessary, like reduce, right? If unlike find the least common denominator, I'm just going to say find the LCD and repeat the steps above. So they are the same in all which ways there. They're also the same when people don't like fractions. But irrational expressions feel a little more rewarding than fractions in general because it feels like you're actually doing something with them. Whereas fractions just feel like they're in the way because this is the problem in and of itself. And we're doing factoring and stuff. And we all like factoring when we know how to do it. All right, guys, I'm going to go ahead and get started. We have up to problem number, I think it was 58. Let's see. We have to, yeah, problem number 58 to do here. So a little bit to take care of. I want to go ahead and get started, if you don't mind. Let's go. All right, in exercises 3 through 8, they say find the sum or difference. Now, all of these ones, when I'm looking from 3 to 8, look like they all have common denominators. So this should be a pretty straightforward process. The thing we have to remind ourselves to do, though, is simplify afterward, if able. We share a common 4x, so I get to add the 15 and 5. I'm not going to be precious about it after this problem, but I'll begin this one by showing, yes, you do add 15 with 5, keep the 4x. So we get 20 over 4x. Now, this could reduce because we could divide top and bottom by 4. So this becomes 5 over x ultimately when you do that reduction. Number 4, 16x squared is shared on bottom with this x here. And then there's a 4 here. Now, one thing you don't want to do here is you don't want to turn this. You don't want to turn this into, you don't want to cancel out these x's and reduce this into 1/4 because now you just lost your common denominator. The whole goal is to have a common denominator through the subtraction. So do keep this as is, and if there's something to change after that, we'll go ahead and do so. This is x minus 4 over 16x squared. I wasn't being precious about it. These just can't combine. And nothing can reduce now. So we just leave it like that. And that's all we can say. On number 5, always try and look beforehand and see if there's a way to do some sort of reduction afterward, but no dice. 9 over x plus 1 minus 2x over x plus 1. See, that is different from multiplication with and division, but 9 minus 2x over x plus 1, again, there's nothing I can really do there. Seek common factors if they exist, but they don't. But that's the difference between this and multiplication division, like I said, is I don't want to simplify these things right here early on. I want to keep that common denominator. Multiplication division, you want to take care of as much as possible because it's not about a common denominator. You're about to multiply or divide those things, and you're going to multiply and divide every single portion of that, ultimately. Okay, here, we'll combine them through addition, or well, not combine, but we'll write them as one fraction. And the top has a common factor of 3x. If you factor that, you get x plus 2. Your, I wouldn't say hope, but what you'll seek after that is, can anything now cancel on top and bottom? The answer is no. If this was an x minus 8 here, boom, they'd go away. But right here, we'll write it and leave it like that. This is an acceptable answer, and honestly, this is an acceptable answer as well, either or. The factoring is my effort to see if something could, cancel on top and bottom. Nothing could, but I don't want to waste my effort and erase it afterwards, so it's accepted to write it as a factored form as well. Is it preferred? In some cases it could be, but this is fine. 5x over x plus 3 plus 15 over x plus 3. I'm sniffing something different on this problem where we do get 5x plus 15 doesn't combine, but 5 is a common factor, and you're left with x plus 3. So this is a case where on top and bottom, something does clean up, and this is why we do the factorization check. So we're left with 5 as our answer. Now, like previous questions, we will list exclusions when something cancels. So, and I'm getting more accepting of their habit of doing that for these cases, so we're not doing it for every problem under the sun. I get it. But yeah, we're listing x can't equal -3 because this is supposed to be equivalent to this. This is 5. Whenever you plug in anything for x, you're always going to get 5 out. When you plug in -3, you get an indeterminate 0 over 0. So it works for everything but -3. Number 8. Little poots. 4x squared over 2x minus 1. I already see where this is going. Minus 1 over 2x minus 1. This becomes 4x squared minus 1 over 2x minus 1. And make no mistake, this is a difference of two squares. This factors into 2x minus 1 times 2x plus 1. And guess what? There's a 2x minus 1 on bottom. So, gone, go these. You're left with 2x plus 1 as a result. Now, there is a restriction because of the things that canceled. When we look at this, 2x minus 1 can't equal 0. When you add 1 to both sides and divide both sides by 2, x can't equal 1/2. And that's our restriction there. Okay. All right. Before we practice the common denominator things, we're going to practice least common multiples. They say find the least common multiple of the expressions. So on number 9, we're going to find the least common multiple of, and these aren't numbers, these are polynomial expressions. But what you notice here, and I'm going to write LCM there, sorry. You'll notice here that they each share a 3, but this guy's missing an x, and this guy's missing an x minus 2. So they both share the 3. We need the x and the x minus 2 as a togetherness thing. This would be the least common multiple of both. We don't multiply an extra 3 into this and an extra 3 into that when they both already share that same 3. We only multiply what's missing in the other guy. That's what we're going for. Number 10. For the least common multiple of 2x squared and 4x plus 12, what you probably want to first do in 4x plus 12 is factor out the 4, and you're left with x plus 3. Now, for the 2x squared, you can see that I would need to multiply an extra 2 here to match that 4, and I need to get that x plus 3 in the fold as well, because it doesn't have an x plus 3. This is totally missing an x squared. But when put together, this is what we'll have. 4 times x squared times x plus 3. I don't know if there's a better or worse way to write what it is I'm writing. What I will say is what I'm doing in green is a little bit of what I'm going to do when we get the common denominator stuff for fractions. This case is we're just writing out the least common multiple and not doing the whole multiply top and bottom by this. It's a little wonky for me to get my explanation in, I feel. Especially when nothing factors and it's already factored. I feel like there's something missing in that. Number 11. Got to find the least common multiple of 2x and 2x times x minus 5. Well, they both share a 2x, and this one's missing x minus 5. So, literally, 2x times x minus 5 is the least common multiple. That you need to just multiply this guy by x minus 5, and they're common. They're the same thing. It's like least common multiple of 3 and 6. Just multiply 3 times 2. You don't have to do anything with the 6. Number 12. Now, one thing the book will do slightly differently, and I hope it's okay that I'm not really changing my numbers too much. I'll explain what I mean on this problem here. But I'm not changing my numbers too much, meaning I'm not breaking down 24 into 2 cubed times 3 and things like that. I know the book's going to do a lot of that. As long as there's nothing to factor polynomial-wise, common factor-wise, I'm not really doing anything there. This one I do. This is a 16x, by the way. 8x squared minus 16x, I can factor an 8x out, and I get x minus 2. And that stands to importance for us when we write this one. So like I said, I'm not splitting up 24x. Well, listen, I'll do it for this problem, just to kind of explain what I'm doing. 24x squared also has an 8x and a 3x right there. And I only bring that up to just show that they both share an 8x. But this one's got a 3x that this don't, and this one's got an x minus 2 that this don't. So we're just multiplying what's missing in either one, and when collectively together, in a factored form, if you will, we would write this as 24x squared times x minus 2. I don't think they need us to distribute that. Ultimately, we don't want it distributed. We want it factored, and this is technically factored. But we don't want to break up 24 into 8 times 3 or 2 times 2 times 2 times 3 and x squared into x times x, etc. Just the unique factors are written differently. So number 13, we need the least common multiple of this difference of two squares and this linear binomial. You can probably see where this is going. I can see what's happening. This is x minus 5 times x plus 5. So that's the answer. This one is missing the x plus 5. This one's got the x minus 5 that this has got. So the answer is x minus 5 times x plus 5. That is the least common multiple of both of those. And they don't have a clue. Okay. I also have a difference of two squares here. The other one, not so much. These two quantities remind me more of what we're probably going to be doing in some of the common denominator questions, ultimately. Something kind of bigger than. Like I got a quadratic here to take care of. and I got a quadratic here to take up. And my guess is this is sharing either, that there is a 3x clearly. It's either sharing the 3x minus 4 or the 3x plus 4. In this case, it's got to be the minus 1, negative 3, plus 4 is positive 1. So it's going to be the 3x plus 4 that these ones share. So they both share this. What's missing is this guy in that term and this guy in that term. So as a collective whole, we have 3x minus 4, 3x plus 4, and x minus 1. Those are all three factors that could be shared among all of them without doubling up on the x plus 4s. Right? We don't want to square it. We just want to have one instance of it. And then we're squared away. We're good to go. Number 15. Oh, I was going to say, it looks like we went a little backwards on this one, but this one's just, I'm not going to say it's mean. This one doesn't have what you'd expect here. You might anticipate this has an x minus 8 in it, but it doesn't. It has an x plus 8. So that is this one, and that is this one right here. Nothing is shared among them. So this needs both of these, and this needs that one. So this needs all three of these together. The least common, this is one of the first, probably the only instance we're going to see here, that the least common multiple is this times this. It's everything together. It's like least common multiple of 3 and 8. There's nothing before 24, 3 times 8, that you get. Number 16. Actually, 16 might be more of the same. Oh, no, it's not. 16 looks to be back to form. So the least common multiple of x squared minus 2x minus 63 and x plus 7. I need to get more rest these days, man. I'm just yawning. This guy factors here. I'm not going to show extra work. This thing factors into x minus 9 times x plus 7. And if you notice, this one also has an x plus 7. Therefore, that is shared. Therefore, that's the least common multiple. So these are good practices for us getting common denominators in eventuality. Looks like we got to first at least do some error analysis, and then we'll probably jump into those problems. Yes, we will. Okay. In exercises 17 and 18, describe and correct the error in finding the sum. So we are going to have to correct it afterward. So, well, looks like we're doing common denominator things before doing common denominator questions. They're showing us an error, and we got to take care of it. They literally added straight across, and 2 plus 4 would add if this is a common denominator, but it's not. And this is not how denominators work. When adding and subtracting fractions, well, I guess adding in this case, unlike denominators, do not add together. You need to force them alike, then keep them the same, and add the top. So it's interesting that these questions are kind of coming before the actual questions where we have to do common denominators, because this is now a question where we have to do common denominator, literally. So this is part of our practice. Here we go. So we find what's missing. This is missing an extra 5. This is missing an extra x. Together, they make 5x squared on bottom. X times 5x is 5x squared. X squared times 5 is 5x squared. On top, we get 2x plus 4 times 5, 20, and they both are divided by 5x squared. Now that we have these two, like this, we can now write them as a single fraction. 2x plus 20 over 5x squared. Now 2 can factor out, and you get x plus 10 over said 5x squared. Nothing further reduces, but we still gave it a shot, and voila. Et le voilà. There's nothing else that we can do. But anyway, that's the final result. No restrictions, no exclusions outside of x can't equal 0, but we already know that because it's implied. Number 18. Number 18, they go for common denominator route in the way that you're supposed to. You got to multiply those two bottom things together because that's what's missing in each of them, and I get that. But the top didn't change. So while they multiplied the two denominator quantities, and in effect also found the least common denominator, they didn't do anything to the top values, to the numerators. The numerators have to be affected by those same denominator values. Whatever's missing on bottom needs to be multiplied on top as well. So when we do x over x plus 2 plus 4 over x minus 5, it's true. It's true that this guy's missing an x minus 5 here, but you also got to do it on top. And it's true that this is missing an x plus 2 here, but it's also got to be written on top. So we have to still do that full distribution of these things. X needs to multiply with these two. 4 needs to multiply with these two. You do have that denominator. We're all good on that bottom. We have x plus 2 times x minus 5. They're correct. But there was just more to be had. Let's check it out. We got x times x minus 5, which becomes x squared minus 5x, plus 4x plus 8. So this becomes x squared minus x plus 8, which cannot factor. And this divided by x plus 2 times x minus 5. So nothing canceled, no exclusions to mention. That's our final result of that one. So we're going to be doing a lot more of those. Again, I kind of find it interesting that in the error analysis, we haven't done questions like it. And now suddenly we're going to do questions like it. So whatever. Let's get going. Okay, on numbers 19 to 26, find the sum or difference. I think this is where a lot of the money is made in this section. This is where you got to be able to do your addition and subtraction. Now, if you just missed the last two questions, maybe you skipped on by them, you weren't assigned them, what have you. These two questions we actually had to find common denominators with. So if you want to hear a little bit more about it, if I go a little too quickly this time, I apologize. That's what we're looking for. All right, each of these share a common factor of x, but the 6 and the 5 have a least common multiple, really, of 30. So this needs an extra 5 that this don't got. This needs an extra 6 that this don't got. 6 times 12 is 72. 5 times 7 is 35, and we're subtracting the result, 72 minus 35, and this is over 6 times 5x, which is 30x. 72 minus 35 is 37, so we get 37 over 30x, which cannot reduce. We're just done. We're finished with that. Kind of random numbers, but doesn't make it not the answer. Number 20, we go to addition. I would have thought addition and subtraction would have been different sets. I'm glad that they're actually just together. Now, these are monomials. They're not as fun as when we hit binomials and furthermore quadratics. But these ones here, again, this has an extra x. This is x squared is x times x. So I need an extra x going on here, but I also need a little more. 3 and 4 have a least common multiple of 12. So I got to multiply a 3 there as well. This needs some 3x's to make 12x squared. To make 12x squared here, I got to multiply by 4. That ends up being our least common denominator. So 4 times 8 plus 15x here. It all divides by 12x squared. I mean, that could almost be the answer there. I'm going to rewrite the 15x first. It was really close for this to have a little bit more of something. 32. If 32, for example, could divide by 3, which it can't. If it was 33, then I'd factor a 3 out of here, and it could reduce with the 12 and get a quarter. But it can't. We're just going to leave it like that. That's actually all we can do. Very close to extra simplification, and I guarantee you we're going to get there in some problems in a moment. Number 21. 21 is going to be treated a lot like 18 from the error analysis step. There's one different thing here, and it's the subtraction. Okay, so on this problem, what's missing in the other term is that binomial. This x plus 4 needs, well, an x plus 6 to have a good day, and this needs an x plus 4. Like that. Now, I'm going to distribute across the top, not across the bottom. Leave the bottom exactly as is as we do the rest of this. We have x plus 6 times x plus 4, and then 3 gets to distribute into these two to get 3x plus 18. Here's the trick. This is a negative 1 distributing into here, or a negative distributing into 1 times that. Negative 1 times x, negative 1 times 4. That's the tricky part about it. A lot of people will write the minus x plus 4. And forget that this has to be subtracted right there. So be very, 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 very careful. All right, 3x minus x is 2x, and 18 minus 4 is 14. So there's a little bit extra that I can factor. It doesn't seem to ultimately lead to any cancellation, but it's worth trying, and in some cases worth writing. In that way, I will write the answer like that. But nothing could ultimately cancel beyond that. That is number 21. Number 22, I guess an easier problem because we now have addition. So we don't have to worry about distributing a negative. So 9 over x minus 3 plus 2x over x plus 1. This is missing an x minus 3. This is missing an x plus 1. So on bottom, we have a common denominator, x plus 1 times x minus 3 now. 9 times the quantity x plus 1 is 9x plus 9. 2x times the quantity x minus 3 is 2x squared minus 6x. Let's rewrite it in standard form and combine like terms. I'll get the 2x squared first. 9x minus 6x is here, and then we got a plus 9. It is our job to check and see if this can factor, and if through factorization we can get more cleanup. No. This cannot clean up more than this. This is not factorable. It's whether you understand your factoring stuff or not, you can give it a shot. It's not going to work. That's it. Okay, number 23. 23 is where we got to get some factoring biz taken care of first, at least if you do what I do on that method number 2. It's really the preferred method to me. Find the least common multiple by factoring here and seeing what's missing in the other term, so you don't multiply more than you have to. So, x squared plus 5x minus 24 can factor into x plus 8 times x minus 3. And if you notice, this guy has an x minus 3 as well, so that's already taken care of on both of these. That means I don't have to multiply anything extra in this left fraction, but I do need to multiply an x plus 8 in this right fraction to get the common denominator. So I don't need to do more, I need to do less. So on bottom, we now have a common denominator of x plus 8 times x minus 3. Leave it as such as we keep this 12 and add 3x plus 24. And then they combine to this. And you can factor 3 out and get x plus 12. It doesn't look like it does anything regarding cancellation, but we'll leave it like that. And again, this is an acceptable answer here. I want to keep reminding you that as long as nothing could cancel, then the the distributed version, the non-factored version is accepted. But it's worth trying and testing, so we write that. All right, number 24. We have x squared minus 5. Even if this could factor, don't try to. Even if there was a difference of 2 squares, you want the top to be as it is. You want to factor the bottom. Our goal is to find a least common denominator. Okay. On the left side, we have a factorization that is x plus 7 times x minus 2. This also shares said x plus 7. Let's write in parentheses right now because we're about to multiply these by some additional x minus 2's. This gets our common denominator going. The real struggle part about this problem, though, is the subtraction. So on bottom, I have this whole x plus 7 times x minus 2, right? On top, I still have this x squared minus 5. Now, I'm going to subtract this result. However, I might want to write this in parentheses still, the whole thing, through foiling so we can then distribute the negative afterward. It might take an extra step, but it might be exactly what you need to make this happen. Maybe later, I'll skip this extra step. But I got x squared minus 2x plus 3x is plus x, and then minus 6. However, we're now going to distribute that negative. That becomes x squared minus 5 minus x squared minus x plus 6. So you distribute the negative ultimately, that you subtract the entire thing that's being distributed. That's where, again, people tend to make mistakes. X squared minus x squared actually is 0. And negative 5 plus 6 is 1. You have negative x plus 1 over x plus 7 times x minus 2. Now, if we are in the camp of factoring things, including common factors to see if something can cancel or not, even though it's probably clear that nothing can cancel, it wouldn't behoove myself or the book to actually factor out a negative from that top and rewrite it as x plus 1 right there to make sure all is good. So as fine as this answer is, this one is also fine. I actually don't prefer writing this, though. I'd prefer writing the negative out in front. Negatives trick people a little bit, especially with fractions and where they can belong. And this is an example of something that you can also write or perceive. Whoopsie, that should be a 2. Or something else you can also perceive as an answer that is correct. Oh, I'm sorry. This should be a minus here. This should be a minus here. But something that you can also perceive as correct, and this is among them. My preferred answer is this bottom one. I know it comes from a place of trickery as far as how'd you get there, where did the parentheses go, why is the minus only blah, blah, blah. But that's also how this thing can work. The fraction can be negative, provided that you factored a negative out of somewhere, and you don't lead with, you don't have leading terms be negative. You don't. That's just one of the things. It's the same reason why I factored out this 3, right? You just, if there's a common factor, you factor it out. I had a -1 that was a common factor. We've played with factoring negatives a lot, so I shouldn't over-explain that, but just to say this is an accepted answer, that's kind of a weirder version of what I also think here is an accepted answer. Because here's the thing, if there was an x minus 1 down there, I'd want to cancel it, and there wasn't one, but I'd want to seek it out, and yeah, we're good. All right, 25 and 26 have the daring effort of finding a least common denominator among 3 fractions. 3 rational terms. Okay. Straight up, nothing can factor on bottom, so whatever's missing in the other guy is what we got to multiply by. Case in point, I got to multiply this top and bottom by x times 3x minus 1. I didn't give myself quite enough space to write what I want to write here. I got to multiply this by x minus 4 times 3x minus 1. Guys, there's going to be a lot to do on this problem. And I got to multiply this times x and x minus 4. So on bottom are all 3 factors, right? We have x, x minus 4, and 3x minus 1. On top, we got to multiply, and I should get the ball rolling now, x plus 2 times 3x minus 1 times x. Let's see if I can get that all in one fell swoop right now. X plus 2 times 3x minus 1 becomes 3x squared plus 6x minus x is plus 5x, and then minus 2. But it's all multiplying by x, so I'm going to turn that into 3x cubed plus 5x squared minus 2x. Boom, all that's distributed right there. 2 doubles up these ones here. So x minus 4 times 3x minus 1 becomes 3x squared, doubled is 6x squared. Minus 12x minus 1x is minus 13x, doubled is minus 26x. Plus 4 doubled is plus 8. And then we have, this is going to look a little asymmetrical here. I wonder if something will cancel afterward. Plus, this is 5x squared times x minus 4. So 5x cubed minus 20x squared. Okay, that's a lot. That's a lot. Okay, we can now combine like terms. We have a 3x cubed plus 5x cubed, which is 8x cubed. I'm going to cross things out as I go. They're not canceling. I'm just seeing things. 5x squared plus 6x squared is 11x squared. Minus 20x squared is negative 9x squared. So those are gone. Negative 2x minus 26x is negative 28x. Oops, just negative 28x. And then I have this plus 8. Plus 8. And I think that's all. Okay, I don't see anything that can factor. I don't see factoring by grouping. And I don't see a common factor. And it would be incredibly mean if this thing had rational root theorem factoring and I couldn't catch on to it. Even if it did, I can't imagine. Maybe x minus 4, but outside of that, I can't imagine the 3x minus 1 exists. Well, it can't. So I'm going to just say that that's the final answer. We haven't seen a cancellation version of a problem yet, so I'm going to say that we're done with it there. But that, we had a lot to do on that set. All right, number 26. Listen, I'm going to do one step ahead of this problem. You see the problem right there. I'm going to give myself some space on this thing, and automatically right now, x squared minus 25, guys, I'm going to factor it right now just to get the ball rolling so we can start talking about the common denominators here and now. This one's a little tricky because it has this minus on this part of the problem, but we got a deal. Okay, so, well, here's the thing. I don't need the space. Oh, I do. Actually, I do. Okay, what's missing in each fraction? This x minus 5 times x plus 5. These are shared. Nothing else is shared elsewhere. So this is missing an x plus 3 on top and bottom because this got it. And this is missing x plus 5 and x plus 3. So there's a lot of work to do on this problem here. And this is missing It's missing x minus 5 and x plus 5. For me, I might want to just write that as x squared minus 25 just to get that going. In fact, I might just want to do that. That's an x plus 5. I hope that's okay. I might just want to do that even for some of these. You know this x plus 5 times x plus 3? I might as well distribute it now, right, and turn it into x squared plus 8x plus 15. Let's just get it going. I generally don't do that because I write the same thing on top and bottom, but this is the same thing. It's just a distributed version, again, to get the ball rolling. Now, we still have to do some more distribution. We ain't quite done here, but I want to try and save some steps. X plus 3 times x plus 3 is x squared plus 6x plus 9. Now, there's a subtraction here. So there's a lot to be done still on this stage. I'm going to do this in 2 steps just so I don't make a mistake. I got to distribute x with these and get x cubed plus 8x squared plus 15x, and distribute a negative 1 to get minus x squared minus 8x minus 15. And then here, I already distributed the difference of 2 squares, so this is 3x squared minus 75. Now, remember, this subtraction of this thing, which I still got to combine like terms inside, but the subtraction of that thing means all the signs change. And on bottom, I have x plus 3 times x minus 5 times x plus 5. Whew, that's a lot. Okay, I got, listen, x squared, I don't know if it helps or hurts, but I'm going to combine things that I can combine already right now on this side and this side. X squared plus 3x squared is 4x squared. 6x stands alone in that set. And 9 minus 75 is negative 66, right? I think. And then here, I'm going to distribute the negative into these as I combine like terms. X cubed stands alone, so I'll subtract x cubed. 8x squared minus 1x squared is 7x squared, so now I'm going to make it negative 7x squared. 15x minus 8x is 7x, so I'll make it negative 7x. And negative 15 stands alone, subtract a negative becomes a positive, so plus 15. So trying to save some steps along the way. I hope it's okay that I'm doing that. Now we combine like terms ultimately and see if there's anything of factorization. Negative x cubed, 4x squared minus 7x squared is negative 3x squared. 6x minus 7x is negative x, and negative 66 plus 15 is negative 51. When is a better time? First of all, nothing can factor by grouping, and 51 is 17 times 3, and I don't, well, I'm just wondering, I'd have to factor out a negative to know for sure. Oh, if they're all positive, I don't think anything can factor there. I don't think it's worth getting going and trying. But you know what's worth doing? Factoring that negative out of top. What better time to factor out a negative than when every term is negative up top? I'm going to make the fraction negative by factoring the negative out of every term in the numerator and make it x cubed plus 3x squared plus x plus 51. Oh, that looks so much better to me personally. I'm all for that. Yeah, there's no way that that can factor with all these terms being positive and with that being a 1x. There's just no way that that's going to be the case. So I'm just going to believe that's the final answer. We're good to go. So nothing canceled along the way. It was none of that validating stuff that I like to get from those problems. Maybe they'll show up later. All right. In exercises 27 and 28, tell whether the statement is always, sometimes, or never true and explain. On number 27, it says the least common denominator of two rational expressions is the product of the denominators. And sometimes we just saw a bunch of instances where that's not necessarily true. If one shares a common factor with the other, then it's something smaller. Sometimes, when they have no common factors, this is true when they don't share any common factors. I'm not really, so, you know, like x plus 2 and x minus 3, whatever. However, this is not true when they share a common factor. I mean, we just saw a bunch of those, right? X squared minus 25 had x minus 5 and x plus 5. It shared one with the x minus, whichever it was, the x minus 5 that was there. So you don't just multiply the other side by x squared minus 25 and that one by that. So sometimes yes, sometimes no. Number 28, the least common denominator of two rational expressions will have a degree greater than or equal to that of the denominator with the higher degree. That's always true. So if you have, you know, if I have an x squared here and an x cubed here, and I want to find the least common denominator, I'm at least going to be at x cubed, right? It can't go down to x squared or anything like that. So it's just always, because the least common denominator How do I say it to my students? When I say, if I want to find the greatest common factor, I say pull out the smallest degree among all your terms, your factors. The least, so this is the opposite way. The least common denominator is the highest degree among all different quantities. I mean, I don't really know how to explain more of it, but you know, again, if I have an x squared and an x cubed, I have to bring it up to at least x cubed. If I was finding greatest common factor of x cubed and x squared, it would be x squared. It's the smaller of the two, but this is the opposite. All right, number 29, analyzing equations. How would you begin to rewrite the function g of x equals 4x plus 1 to obtain over x plus 2 to obtain this form here? How would I do it? I would use the division, but they're talking about doing the inspection, I believe they called it. If you saw the lecture portion, you know what I'm talking about. So let's see what they want to talk about here. I want to try and do this myself first before I look at their options. What I want to do is I want to basically turn one of these things into 4 times x plus 2, which is 4x plus 8. And 1 is 8 minus 7. So if I turn this into a minus 7 there, that would do what I'm trying to get done. I hope you're recognizing what I'm doing there. It's kind of weird because I'm not writing the second step. Maybe I should. But the second step comes into the fray because I got to multiply by x plus 2. I guess I just got to distribute it into the 4. So x plus 2 distributed into 4 is 4x plus 8. And 8 minus 7 is 1. And that's how we write what we write so we can factor it out. The goal of factoring that out is to then split this into the x plus 2. It is a common denominator. And split it, treat it as such there so you can then cancel this like that. So what did they say? How would you begin to rewrite it? I would rewrite it here. Here's their first, I think this is what they're talking about. That is, looks like option A. Option B doesn't work. That's 4x plus 8 plus 1. That's 4x plus 9. That's not the same thing. Option C, that might be 4x plus 1, but that doesn't... This C works in its own right, but it doesn't work in the way that we want it to. If we split this up into the, this kind of way right here, it would be x plus 2 over x plus 2 plus 3x minus 1 over x plus 2. And these would, don't write cancel, but these would become 1. This would become 1 plus 3x minus 1 over x plus 2. The problem with this is, although this is a quotient, this has a variable in it. So C is in its own right something that it fits the idea. It is 4x plus 1 as a whole, and you're left with a quotient, but that a value is not a constant. So C doesn't work because of that. D, this is 4x plus 1, yes, but this doesn't cancel anything on top and bottom. You can't just take the x plus 2s and make them go away like that. That's not quite how it works. So A is the correct option there. And it looks like we're about to get into these. Well, not yet. Number 30. How would you begin to rewrite the function g of x equals x over x minus 5 to obtain the form here? I was going to say it's in the form, but it's not because that's an x. So let me try and do this on my own as well. G of x equals x over x minus 5. I need to get an x minus 5 out from here, meaning I need to get an x minus 5, and I need to do something here to make it so that the x, so plus 5, like that, because negative 5 plus 5 is 0. So I would start like that, and then I could do the split. So this is probably the option we're looking for. Maybe it's in parentheses, I don't know. I would do B. They didn't put in parentheses, but the goal is you can't cancel yet. You can split it up as two denominators and then do the, and don't call it cancel. X minus 5 over x minus 5 is 1, right? So this ends up becoming 1 plus 5 over x minus 5 when you split up the denominator into two parts. And I know I'm overstepping on the problem there, but I don't want you to think that it's cancellation that's happening. A, C, and D just aren't correct. For whatever reason under the sun, you can see. So based on what we're doing, we're about to get ready to probably do problems like this. Here they are. Now they are going to have us graph, and I mentioned in the lecture portion, I'm not going to slowly explain how we graph anymore. When it's graphed, I'm going to sketch it. And I'm going to get my graph axes ready. So get this thing ready. for the problem. Okay, so on number 31, hold on. Okay, on number 31, I have g of x equals 5x minus 7 over x minus 1. Now, my goal here is to create an x minus 1 in this staging here, but I got a 5x to deal with here. So x minus 1 times 5 is 5x minus 5. Now I got to make sure I turn this thing into negative 7, so I got to subtract 2 from it. This might be a little bit confusing, but hopefully you'll see what I'm doing with this afterward, and we can come up with how to talk about it later. So I factor out a 5 to get that x minus 1, and now we can split this up into 2 different fractions, so those x minus 1s can, well, cancel. And now that those are gone from here, that's just a 5. In terms of writing it in this other form, I'm going to write the negative 2 over x minus 1 first. So this is negative 2 over x minus 1 and plus 5. So this is a rewrite of that. Do I prefer this over long division? No. Or synthetic division? No. I prefer the division version of that. But this also works out. My inspection in going from this step to this step is the most critical portion, because everything else follows suit with regard to the factoring and the splitting. That's all good. But how we create that is just a matter of, I need x minus 1 to be a common factor here. So I'm going to distribute x minus 1 into this coefficient. I think that's how I'm going to explain it from these ones. So again, I'm not going to give myself a long explanation on how I get this graph done. I'm just going to get it prepped, set up, and ready to go. So I got a vertical asymptote at x equals 1, a horizontal asymptote at y equals 5, and a negative 2 is my a value, which I divide these numbers by. Negative 2 divided by 1, and 2, and 4, and 8, which is a quarter. Divide by 1/2 to get 4, divide by a quarter to get 8. 8 down from 5 is negative 3. And same thing on this side here. Divide by negative 1, divide by negative 2, and negative 4, and negative 8. And divide by negative 1/2 there. Okay, so this is the graph. Without a table. And I don't know at what stage they end up not using a table as well. I don't recall them showing a table when they did the lecture portion. Maybe at some point they're like, yeah, you know, you go without it. You do the translations, you understand how the negative 2 works. They do it exactly as I would. My curve ain't doing too hot. I apologize for that. But the idea of the graph is in place. They do say, describe it as a transformation of the graph f of x equals a over x. Now, I didn't, and I saw in the lecture portion they did this, and I should be doing it as well. I should state what f of x actually is, but it's going to be written kind of strange because it's in type format. The graph of g is a and all of these are just translations, is a translation 1 unit right and 5 units up of f, or from f. Now, f is f of x equals negative 2 over x. See, we're keeping that same negative 2 that you had from before. Make no mistake, we are still using that one. But that's how that one's going to be written. Okay, number 32. So yeah, these might take a moment. All right, g of x equals 6x plus 4 over x plus 5. Let's fit this into place so we know how much room we have. Okay. X plus 5 can multiply into the 6, right? That's our goal. We want to write it as 6x plus 30. That's the distribution. And we got to turn this back into 4. So 30 minus 26 would give us 4. I wouldn't mind just writing it as 6 times x plus 5, but you just got to know that it's a 30 so we can figure out what to subtract to make it 4 again. Now, on this stage, I might skip a step here and go straight into the 2 different fractions. Factor out this, split it up with this fraction, and this fraction here. So I'm splitting it up while factoring. The goal is that these go away. And now I have, and this is not going to be as fun to graph, but negative 26 over x plus 5 plus 6. So there's the rewrite of this equation. We are now going to graph it, where we have a vertical asymptote at negative 5, horizontal asymptote at 6. And negative 26 is our a value. Dividing it by 1 is negative 26. That don't fit. Divide it by 2, you get negative 13. And 13 down from 6 is negative 7. 26 don't divide by very many things. It divides by 2. And nothing else really after that is very good. Divided by 4, you get 6.5. Maybe I can just deal with that one. 1, 2, 3, 4, 5, 6.5 right here. So that means divided by 6.5, you get 4. I want to try and double up on those whenever I can. Divided by 6.5, you get 4. So I'm going to get those ones and then divided by 13 to get 2. How about that? So 13 over is at 8, and then you get 2 right there. So there are a couple points at least I can get for myself for this part of this graph. I don't know about the other side. I guess that's where the 4.5 and stuff come into play. Not my best idea of this curve. It should probably approach a little more like that. Maybe somewhere in between. I don't know. Anyway, so there's that one. These really won't fit here. 6.5 over is 4 up. Probably somewhere right there. And 4 over is 6.5 up. So this curve ain't curving the way that I'd want it to, but there we have it. Okay, the graph of G is a translation 5 units left and 6 units up from f of x equals negative 26 over x. Okay. Number 33. Okay. You want to multiply 12 by x minus 5 on top, so you have the common factor that you can factor 12 out of there. So that's 12x minus 60. We got to add another 60 back to negate those to get it back to 12x all over again. So there's our setup. In order to now do this, we factor out 12 from here to have that x minus 5. It's going to be over an x minus 5, and so is that 60. Also going to be an over an x minus 5. Very big number in 60. I might have to change my scales on these things. They haven't learned their lesson in the book. X minus 5s go away here. You have 60 over x minus 5 plus 12. Very inventive way to do this stuff. I never really would have thought about doing it this method, and I still don't think about this every day. I'd much rather do the division, but we're working addition and subtraction in their own way, I guess. So yeah, I want to change the scales anyway because this 12. So let's go by 6s. If I go by 6s, that might work out. So if I go by 6s, I get 30. Now, pardon me as I slow down with the points I want to plot. I said I want to go quickly, but I can only go the speed that the problem allows me to. And the scale that I have. If you're using the same graph paper as I am, and I guess I got to attach the graph paper. I totally forgot. I'm going to have to attach this for these ones. If I'm going by 6s, the 5 over is going to be a little bizarre. That's not going to be my favorite thing to do, but I have to deal. So, if I x's I go by 5s, that would be really weird. It'd probably be preferred though. 5 to the right, it's 5/6 of the way over, and 12 up is like that. So, sadly for the x's, we're going to have to do what we do. Now, when I go 1 over, I can go 60 up. I still can't even fit that there because 60 up is at 70, but I'm going to pretend like I can. If I go 2 over, I go 30 up. 2 over is like here. It's 1/6 of the way over. So again, things are going to get kind of weird. So I'm at 40. Oh, I'm sorry. Hold on a second. These aren't multiples of 5. These are multiples of 6. So, oh man, give me a moment, because I'm at 12. I'm at 12 here, so 60 up from 12 is 72. So okay, so that's at the 12 mark. But this next one, two over, I go 30 up. Oh, 30 up is 5 of these. It's 3, 4, 5. Maybe I did that last time. I just forgot where I was. 3 over, I go 20 up. This one will be kind of in a bizarro way. 18, 20 is probably going to be about right there. 4 away, I can go 15 up. 4 away. 4 away would be halfway, right? From 5/6 to 4 away. I'm sorry, this is me processing this in my own way. This might take a while, guys. 4 away, I go 15 up. So 12 and half boom is 15, boom, like that. So this is really hard to get these scales right. I gotta like really I double dotted this thing. I really got to move these things over as best I can to get them fitting. I just want to pretend like the scale was normal and I'm still getting integers wherever I can. 5 away is 12 up. 12 up from 12 like that. 6 away is 10 up. And 10 is 1 2/3 up from there. And it's at 5/6 away. So that's a lot of different points I'm getting for just that part. And I have to kind of double up on those going this way. So I just went 10 away. Now I go 12 away to go 5 up. This is not fun. I'm basically going to copy and paste this on the other side, just so you know. 12 away is 5 up, and 5 up from 12 is 17. Goodness me. 6, 12, and 5 up like that. Wait, I did 6 away. I didn't do 10 away yet. That was 12 away. 10 away is probably right here. 10 away is 6 up. 15 away is 4 up. Jeez, why am I doing this? Look, it's a curve. It's a curve. 20 away is 3 up. So 6, 12, 18, 19, 20 is halfway up there. So 3 up like that. 30 away is 2 up. 1, 2, 18, 24, 30 is 2 up. And 60 away is 1 up. 60 plus that extra 5 is 1 up like that. Okay. That's a lot just to get some accuracy there. I'm graphing the curve. If these were scaled, if I had a scale that was tall enough to work this thing out, would have been fine. But that's only half of it. I am just going to copy and paste on the other side. I don't know how much you're following me with this anyway. They did ask me to graph it, so I'm trying to be accurate. Okay, I'm going to take that. No, I tried to lock that. Hold on. I'm going to take that and copy and paste and rotate and fit. I don't know where it fits specifically. I got to get this right. Where would this go? That's the only problem, is I don't know exactly where this thing goes now. This is at 5. What was this one? This was 6, 10, 10 away. So what's 10 away from 5 is -5. -5 is over there. So I think I'm actually in the right spot. That point there should be at that spot. So I think I'm pretty much in the right spot there. All right, there's my graph. Sorry about all that, guys. It's their fault. They constructed the problem. The graph, who knew I had to do graphing on this? Think about addition and subtraction. The graph of G is a translation 5 units right and 12 units up from f of x equals 60 over x. Now, what concerns me is I'm going to have more problems like this, given that this is only the third problem in the set, and they tend to get harder or whatever. So looking at these other numbers, some of them get kind of big. So it does concern me that, yeah, we're going to have to do this a little more. Number 34. And I'll stay as accurate as I can plot points. That's my goal. Unless I can keep within that original scale, and it doesn't look like I can on this problem, but we'll see to what extent I have to go. G of x equals 8x over x plus 13. So, oh, shoot. I need to get this graph thing back. Okay. So 8 times 13 is 104. I have to subtract 104 again to negate that and get it back to 8x, which means no good for our graph. Because when I factor, and hopefully you can tell what happens on these now. When I factor 8, I do get the x plus 13. 104 is going to also be dividing by its own x plus 13. That means our a value will be 104. This might be one more of those lost cause kinds of things here where I don't know what 104 divides by. It divides by 2. You know, it doesn't divide by 3 and things like that. So g of x equals negative 104. I mean, I don't know who they're trying to amuse with this. This is not amusing. I get them having us write the equation. I get them even having us describe the transformation. I don't get why they're having us graph these. I don't mind if they give us basic graphs. I'm complaining right now. This is a lot. And I don't even know what to scale by. Tens? I don't even know. So when I say I'll be accurate, I don't know to what level of accuracy. Listen, I can't divide 104 by a lot of numbers. I can divide it by 2 and 4. Therefore, I can divide it by 26 and 52. And I don't know what else I can do beyond that. With the 104s, sure. So these will go by tens. I suppose I got to go by tens here. Oh, whoops. So 50. And like that. I mean, if they were within just the realm of scaling by tens, even by 20s, I'm good. I can work it. This 104, no, these aren't okay problems. Big Ideas Math, please understand that no one cares to graph these. Literally, no one. 8. Oh, I'm sorry. 13 would be, these are going by 10s, right? Not by 5s. So 13 would probably be about like right there. 8 would be 4/5 up toward that. I guess that's as best as I can snap it in place. So 13 left, 8 up, negative 104 is the set. So divide negative 104 by 1, you get negative 104. And 104 down from 8 is negative 96. And going 1 away from 13 is 12. So 12 negative, listen, it's here. You can't see it, but I'm plotting a point right there. It's hugging really closely. Divided by 2, you get, let's see, 11. And you get 52. 52 down from 8 is 44. Wait, 52 down is negative 44. So unfortunately, my scale numbers are going in the way here. So there's another point that's right there that you can't really see. So I got 2 points right there that you can't really see. That's just fantastic. Maybe I should move my numbers over. So that one and that one. Okay, that's much better. Okay, can't divide it by 3. 4 is 26. Divide by 4, you get 26. 4 away from 13 is 9. So that's on this side. 26 down from 8 is negative 18. So negative 18 is about right there. And then I can't really divide by other numbers. Maybe it can divide by, can't divide by 6 or 7, or it can divide by 8. 13. Divide by 8, you get 13. 8 away from 13 is 5, so negative 5 here. And then 13 down from 8 is negative 5. So negative 5 actually is this point right here. So that's kind of a perfect middle value. And then if I can divide it by 8 to get 13, then I can divide it by 13 to get 8. And 13 over, oh, perfect. It crosses through the origin. 13 over from negative 13 is 0. 8 down from 8 is 0. That's the one point that I feel great about with this whole set here. And then we'll divide it by 26 and 52 and 104. So divide by 26 to get 4. 26 over from 13, negative 13 is positive 13. Divide by 26 to get 4, and that's halfway down from 8, so probably about right there. Divided by 52, 52 away from, and I am going to copy and paste this one over on this other side, just like I did from the last problem. 52, divided by 52 to get 2. 52 over from negative 13 is positive 39. So 10, 20, 30, 40, here's 39. And then it's just 2 down from 8 is 6, just a little more than half. And then 104 away from negative 13 is positive 101. Boom, just 101. And then 1 down from there. It's just really nice and tight like that. So I can draw a curve that looks like this. The problem is, as great as I build my points, my curve doesn't look so good anyway. You know what I mean? I'm working towards so much accuracy just for this thing to look like slop in its final form anyway. Okay, let me lock some things in place and copy and paste that thing over. Whatever you're choosing to follow or not is obviously totally up to you. I apologize if you're doing things exactly to what I can do and you're like, oh man, you get to copy and paste and I don't get to copy and paste. Well, you know what? Boo stinking who. it's likely you don't have to do these problems, or you're not doing it this way and you're moving on to the next problem, which is just fantastic. So boo, stinking who. The next thing I want to do is figure out where these actually align. If I need to go 8 over to go 13 up, 8 over from negative 13 is negative 21, 13 up from 8 is 21. So I got to move this up maybe a little bit, maybe over. I'd say this one's the ticket. I don't know. It doesn't really snap in. It's kind of the halfway in between those, and that works out for me. Okay, the graph. 4 up from 8. Yeah, that's fine. All right, the graph of G. These are just translations, but the graph of G is a translation, 13 units left and 8 units up, from the stinking f of x equals negative 104 over x. Where I don't even know what this book, man. It's one of those things where I wonder if they know what they're doing with these problems and who's doing them. If I knew this is what I was signing up for when I said I'd do every problem, you know, it's one of those instances. This isn't even a section on graphing. I hate to gripe. Listen, I'm gonna stop griping. It's not healthy for any of us, especially you watching. You're like, Mr. Robinson, don't you like what you do? Not like this. No, I don't. I am a human after all. I have feelings. All right. Here's the thing with this one. 2 is already common multiple with x. So I can already split this one up into 2x over x plus 3 over x, because here the x's will already cancel. So there's nothing else I have to do with that one. So this problem's fine. This is 3 over x plus 2. This problem is fine. I'm very, very happy for it. I'm very happy to graph this one. I have no problems with this. The vertical asymptote is at x equals 0. The horizontal is at y equals 2. And we use this 3 to mosey on forward as our a value, divided by 1 and 3. And I'll divide it by 2. Divide 3 by 1 to get 3. Divide 3 by 2 to get 1.5. So divided by 1.5 to get 2. I've been doing that more often. Divided by 3 to get 1, and divided by 6 to get 1/2. Divided by 1/2 to get 6. Same thing on the other side. Divided by -1, by -2, heck, by -1.5, and by -3, and by -6, by -1/2. 6 down from there is -4. I can also divide by 12. 1/4 to -1/4 to get -12. I can kind of fit that one. That one kind of goes out of range. Pretend like it's there. But yeah, let's draw a curve with those points in mind. Yeah, I'm fine doing those. I mean, this still is not part of the graphing section, but this was a fine, quick old graph. I can do this a lot faster on paper. Okay, the graph of G is a translation just 2 units up from f of x equals 3 over x, right? It just takes the 3 over x and it just has a little plus 2. Number 36. I think 36 is doing the same thing as 35 is, which isn't uncommon for an even to follow its odd. Which actually makes me hope that 33 and 34 were their own little special, like, hey, they're not going to be as weird anymore. So we'll see. But g of x equals 4x minus 6 over x. These are similar, or this is similar to the last one in the way that 4x can already divide by x on its own. So we can already do this split right now. 4x over x minus 6 over x. Split them up because x over x goes away. And as a rewrite in that other form, we'll get negative 6 over x plus 4. It's also a fine one to graph. Nice and quick. Vertical asymptote is on x equals 0. Horizontal asymptote is y equals 4. And negative 6 is our thing to do. We're going to divide it by 1, 2, 3. Those are good. Divide it by 1. divided by 2 and 3, 4, 5, 6. You can divide it by 1/2 to get 12. 12 down from 4 is negative 8. So that fits. Divided by negative 1 to get positive 6, negative 2 to get positive 3, and so on and so forth. So we'll get a few points from that one. Okay. All right, there's one side. And here's the other side. We're going to number 58, right? All right. Four units up. Negative 6 over x. Okay. All right. Number 37. G of x equals 3x plus 11 over x minus 3. I think we're back into, well, needing to do some extra work to get things canceled correctly because we need an x minus 3 commonly with that 3x. So let's try it this way with the factorization here and now. Let's see how little we can write. 3 times x minus 3, that's 3x minus 9. Negative 9 plus what is 11? 20. Negative 9 plus 20 is 11. See, through distribution, we'd get that. But these are both dividing by their own separate x minus 3s. I could go one step further and not even write that part, but without cancellation. But I don't think I'm going to do all of that. So here we're going to get 20 over x minus 3 plus 3. A little bit bigger. But because these asymptotes are fine, I think I'm going to leave it like this and just not be able to divide 20 by 1. That's good. As long, these are odd numbers, so I want to leave these as is. So x equals 3 is our vertical. Y equals 3 is our horizontal. And let's divide 20 by some numbers here. 20 divided by 1 is 20. I can't fit that. 20 divided by 2 is 10. I can't really fit that either. So I guess numbers aren't great here. But 8, 9, 10, up from there. 20 divided by 4 is 5. Wait, 20 divided by 4 is 1, 2, 3, 4, 5. 20 divided by 5 is 4. Those are really the only ones I can fit very well. Even the other 10 over from there, I just fell off the window range. It's going to be a little separated. That's just how some graphs go. At least I can fit some points. This one I can fit a few more. 20 divided by 2 is 10, and 10 down from 3 is negative 7. So I can actually fit that one. And same thing with the other ones. But 3, 4 is 5, and 5 over is 4 down. And then 10 over is negative 7, and 3 down is right there, which is actually an x-intercept. No, 2 down. 2 down, not 3 down. So it's not an x-intercept. We're at that point right there. Okay, so we got those points. And 20 over would be 1 down, which we didn't quite fit. So graph works. I'll take it. Okay. The graph of G is a translation 3 units right and 3 units up from f of x equals 20 over x. All right, the last one from this set, number 38. The x plus 10 is a little alarming because we have to go 10 units left, and so I can't get any points to the left if I just keep my scale the same. So g of x equals 7x minus 9 over x plus 10. I think we have to do this one in full. Like 7 distributes into x plus 10 and get 7x plus 70. 70 minus 79 would give you negative 9. So that's where I'm going to take these x plus 10s into the fold right there. Actually, let's write it all over a single x plus 10 still because I got one more step to do anyway. So all over x plus 10. And then as we factor 7 out to get the x plus 10, that divides by this x plus 10 and we'll cancel. This minus 79, ooh, that's our a value though. Is 79 a prime number? I can't think of anything 79 can divide by. I'm going to assume it's a prime number. So negative 79 over x plus 10 plus 7. So with this one, the fairness or unfairness of this problem for myself with the graph is that unfairly I can't divide 79 by anything cleanly. other than 1. And I'm not going to try and do something with decimals when my scale is going to have to be a little bit bigger, given that, number 1, it's a 79, and number 2, I have to go left 10. So I will scale these by 10s, but you're not going to see me do a lot on the graphing this time. I'm going to have to deal with, I'm not going to deal with decimals, basically. Stubbornly, I'm not going to deal with decimals. So my asymptotes will go x equals negative 10, because they're scaling by 10s there. Y equals 7, just 7/10 of the way up. Boom, that actually fits pretty well. And listen, it's a negative 79, so I can go 1 over and 79 down, and 79 down from 7 is 72, negative 72. So here's negative 72, where it's just 1 over, like that. So that just looks like a point there. And then I'll go 79 to the right from negative 10, which is 69. And we'll go 1 down from there. So it looks like that. So those are the 2 points you're going to see me slightly plot as this thing works its magic towards something. I don't know what specifically, and I don't pretend like that's it. It may or may not be, but they force my hand. I'll plot those points here to just be nice. 79 up, so 1 over, we go 79 up. 79 up from 7 is 86. And 86 is right there-ish. And then 79 to the left of 10 is 89, negative 89. And we're going 1 up from there, 7 to get like that one, like there. And then we plot our points from that set as well. So, boom. Oh, I got to widen itself out at some point and shrink itself up at some point as well. So, probably do it a little bit more like that. Need a little bit of symmetry. I don't know if that looks good or not. But that's my graph. So, unfair numbers give an unfair looking graph. And there we have it. The graph of G is a translation 10 units left and 7 units up from our f of x. No, we're 7. It's up from f of x equals negative 79 over x. Okay. There we have it. All right. An hour and a half through. Let me get a little water hit before we move forward. Okay. At least these problems seem a little more relevant. We have some complex fractions to deal with. In exercises 39 to 44, simplify the complex fraction. Now, my personal go-to on these problems is to find the common denominator of each portion of the fraction. What I mean by that is I have a numerator and I have a denominator. Clean those up as needed, and you can, if you'd like to, at any point, write that as a division. Like, this is a fraction, but write this divided by that with the division sign. This top, you know what, let me get rid of those parentheses. They're kind of getting in the way, but that's what I'm doing. The top, I can get a common denominator by multiplying 3 over 3. The bottom, I can get a common denominator by multiplying x over x. So on the top, I'll have x minus 18 all over 3. And on the bottom, I'll have 10x plus 4 all over x, like that. And that's what we're trying to deal with there. Now that we have that, we can work the division in a left to right manner. So this is x minus 18 over 3 times x over 10x plus 4. In that, actually, I said I would write the division first, so let's do that. Let's divide it. Let's write it as divided by 10x plus 4 over x, which becomes multiplying by the reciprocal, right? So x minus 18 over 3 times x over 10x plus 4. Okay? Now from there, we try and do, well, it's multiplication now, right? It's not common denominator or anything, but there's a common factor on bottom that I can still deal with, and I plan to. Now, when we do this as a whole thing, we're not trying to distribute anywhere, that we don't need to. We'll just kind of leave it like this. So what I'll do here is I have x times x minus 18 on top. And on bottom, this can factor into 2 times 5x plus 2, and 2 times 3 is 6, so it becomes 6 times 5x plus 2, like that. And then that's as much as I can leave it into. I'm going to leave it like that there. As far as exclusions go, nothing canceled, but remember, x was in a denominator at some point, despite the fact it flipped into the numerator. X still can't equal 0 because it was at one stage in a denominator, even way back when, right here. Okay, number 40. We have 15 minus 2x over x fifths plus 4. 15 minus 2 over x, excuse me. Over. Okay, so the bottom needs a 5 with the 4s and an x with the 15. I think I can go left to right division right now if you're okay with it, because these all divide by x on the top. I got 15x minus 2. And then I can write division here, and on the bottom, they all divide by 5, but I got x plus 20. So if you're good with that, I'm good with that, just kind of writing it as left to right as soon as I can once I get common denominators within their own parts of the fraction. So now I can multiply by, the opposite here, so the reciprocal, times 5 over x plus 20. And nothing here factored. I would have done that actually in the previous step. 5 times 15x minus 2 is something that, let's see, do we clean that up? I think we just leave it factored. If nothing could factor, we don't distribute. So 5 times 15x minus 2 over x times x plus 20. We're all golden there. What we have to check on is, was there anything in a previous denominator that we'd have to address? And I think that answer is no. This was a 5 before, no restrictions there. And any restrictions here are implied to be, 0, negative 20. Are implied on their own. They didn't cancel, so we're good. Okay, number 41. The denominator seems good on the on that bottom, but this numerator has some unlike denominators. Now this one's actually interesting. This is a case where the book mentioned a different method that, well, I don't know. See, the thing is, this 8x minus 20, see, I don't want to rewrite everything. Let's just rewrite it if it's okay. 8x minus 20, I can factor out a 4, and I get 2x minus 5. If y'all notice, all these share 2x minus 5s, right? It's kind of like, hey, if only I got a common... But here's the thing. This part here, we're not about getting common denominators. We're just about canceling things out that will go away. So why don't I just kind of leave that as is? I got to get a common denominator up here, times 4 over 4, and then let's just go to work from that. So despite the fact those are all the same, don't cancel something that you don't know how it cancels yet or not. You don't want to make mistakes. So let's avoid the mistakes. This all divides by 4 times 2x minus 5, where we have a 4 minus 7, right? 4 minus 7. And this is dividing by this x over 2x minus 5, like that. Now, 4 minus 7, of course, is negative 3. So we have negative 3 over 4 times 2x minus 5. And now we multiply by 2x minus 5 over x. Now we can recognize that, okay, 2x minus 5's go away. I think that's it. Now we have negative 3 all over 4x. So that's the final result. Now, as far as restrictions, there was something that canceled and was also in a denominator at one point, so we're treating each of those as such. And 2x minus 5 can't equal 0. If you add 5 and divide by 2, x can't equal 2 fifths, or 5 halves. X can't equal 5 halves. So that's number 41. Number 42 now has the denominator, the bottom set of complex fraction things needs treatment, whereas the top is good. It's all good. So 16 over x minus 2. Unfortunately, I'm ignoring the lines on my binder paper here. I don't know how to write this best. Should I write it super big or super small or somewhere in between? This needs a whole x plus 1 makeover, and this needs a whole x makeover, while we kind of treat the rest as is. So I got 16 over x minus 2. That hasn't changed. Divided by 4x plus, and 6 needs to distribute here, 6x plus 6, all divided by x times x plus 1. Flip it, skip it, see you later, bye. Here, let's write this. 4x plus 6x is 10x, and 10x plus 6. As a common factor there is 2. So when we do this, we are going to flip. We got x times x plus 1 on top, and on bottom, a 2 factors out, and you have 5x plus 3. At least now we can recognize something that can go away. Only one little part. 16 over 2 is 8. Everything else looks like it's going to be exactly as is. So now we have 8x times x, we have 8x times x plus 1 up top. And on bottom, we got an x minus 2 in parentheses and 5x plus 3 because it's a quantity times a quantity. So that times that, all good to go. Now, nothing canceled here to list any issues from that, but from here, these were in the denominator. X can't equal 0, x can't equal -1. Those are two of the restrictions there. Exclusions, if you will. Number 43. Ooh, it's getting big. The top needs no real change. Well, I take it back. There's some factoring we're going to do, just no common denominator work. There are a couple things we can do on the top there. On the bottom, some work to be had. So it's just a bigger problem. You have to give it some time. Just don't make a mistake along the way. Especially, ooh, there's subtraction. Okay, they're going in the big leagues to begin with. I'm not going to do anything massive yet as far as common denominator work. Let's just first get some factoring going on. It's the first time we got to do a lot of factoring beforehand. So here's the thing, guys. 3 can factor out of here, and you get x squared minus 1, right? That actually now becomes a difference of 2 squares, which is x minus 1 times x plus 1. So I'm doing all of that right now for that part of the problem. That's on the top. On the bottom, I still have to factor that denominator portion right here. This factors into x minus 4 times x plus 1, which means this guy here is missing an x minus 4, like so. And there we go. So now what I can do is the whole division process here. This is 1 over this big guy. And this is divided by 5 times the quantity x minus 4 is 5x minus 20. And then minus, now you have to distribute this. You got to be careful. You got to distribute this negative into the x plus 4. So it's minus x minus 4. Now over here we have x minus 4 times x minus, or x plus 1 as a denominator. It's not about getting common denominators. It's just, it is what it is. Let's work some things out internally as well. 5x minus x is 4x. Negative 20 minus 4 is negative 24. So a 4 can factor out of those. So get ready for that. We have 1 over 3 times x minus 1 times x plus 1. And on the flip, we're going to have x minus 4 here, x plus 1 here, and when you factor a 4 out, you get x minus 6 there. So, not much cancels to my knowledge here. This is x plus 1s go away. Boom, boom, like that. And that's all I can see there. So x minus 4, x minus 3 times 4 is 12, though. We're going to have to combine those. So on top, I just have 1 times x minus 4, which is x minus 4. And on bottom, I have 12 times x minus 1 times x minus 6. I think that's it. So from those stages, that's what we got. As far as restrictions go, x can't equal -1. We just saw the cancellation of that. So x can't equal -1. And previously on bottom, we had an x minus 4 and an x plus 1 before it flipped. So x can't equal +4 or negative. Oh, wait, -1 was already canceled. So x can't equal +4 either. So -1 or +4. Okay, there's 43. Number 44, it's probably just as long. Let's go to the next page. Oh, yeah. So number 44, we have this over this. All right. Just to save one step, x squared minus 4 is x minus 2 times x plus 2. So if we're trying to see what's, missing, this guy's missing a whole x plus 2 work. And these are each missing each other. I miss you. I miss you. We shall be one together. Everything here is going to have some form of x squared minus 4 or x minus 2 times x plus 2, which you can see some things will ultimately cancel, which is, it's fine. So as far as the overall division goes, 3 times the quantity x plus 2 is 3x plus 6. We are subtracting the 6 there, which means those will go away. This is x minus 2 times x plus 2. And this is divided by, over here, 3x minus 6 plus 1x plus 1, 2, all over x minus 2 times x plus 2. If at any stage you'd like to cancel out those x minus 2's, x plus 2's, go ahead. But don't make a mistake on how this division actually works itself out. Now the 6's do go away. 3x, let's clean this up first. 3x plus x is 4x, negative 6 plus 2 is negative 4, and 4x minus 4 will factor a 4 out. So I have 3x all over x minus 2 times x plus 2 times, and then x minus 2 times x plus 2 goes up on top here, and on bottom, the 4 that factors out leaves you with an x minus 1. So, gone, gone, and you're left with 3x over 4 times the quantity x minus 1. Now, everything that canceled were also our restricted values, right? They were in the denominator at one point, all that kind of stuff. So x cannot equal 2 or negative 2, plus or minus 2. Okay, number 45, problem solving. The total time t in hours needed to fly from New York to LA and back can be modeled by the equation below, where d is the distance each way, a is the average airplane speed, and j is the average airplane speed of the jet stream. Is jet stream like wind speed? Simplify the equation, then find the total time it takes to fly 2,468 miles. When a is 510 miles per hour, j is 150 miles per hour. Okay, so we got t equals, oh, they're showing kind of pictures. Yeah, jet streams, kind of like headwinds and tailwinds and things like that. Jet stream going against your average jet speed is working against you. So total time, it's distance over rate plus distance over rate. You add the two times together and you get your total time. That totally makes sense. I feel out this thing completely. Let's simplify it though. As far as common denominator goes, let's begin with that. This is missing a couple a minus j's and a plus j's. A Mr. J. Like that. Got to distribute this thing out. So t equals, now d times this is a times d plus d times j. I'm going to put everything alphabetically, so just to be consistent. Plus a times d minus d times j all over a plus j times a minus j. That would be a squared minus j squared, but we're not kind of in that work. dj minus dj is gone. ad plus ad is 2ad. So we have 2ad over a plus j times a minus j. You can argue whether or not this looks more simplified. The bottom line is it's a single fraction. And that's one of our very definitions of simplification. So that's kind of our part A. Our part B says find the total time it takes to fly this many miles. That's D. So how about when D equals 2468? Wait, D is the distance each way. I don't know if that means, well, New York to LA is about 2468 miles. So, well, okay, I guess D is just that number. I guess we don't double it. We don't double it. It'll double here, but that's a different story. A is 510 and J is 115. Okay, let's do a substitution. So we'll get T equals 2 times 2468 times, what, 2468? Yeah. Who do we appreciate, right? Yeah, you know. Oh, but that's D. Whatever. A is right here. They're both on top. That's okay. A plus J, 510 plus 115, and 510 minus 115. Honestly, the bottom might be easier to write 510 squared minus 115 squared. So I'm gonna go to the calculator. I'm gonna do some things. Let's maybe try the let's see, 2 times 2468 times 510. And yeah, on the bottom, it might be better to just write in parentheses 510 squared, a squared minus b squared, right? Squared minus 115 squared. And that should be everything. We get 10.196. This is what, hours? Time in hours? Yeah, so that kind of makes sense as an answer, at least to me. So that's around, I'll say 10.2 hours of flight time. Now, would you get the same answer by substituting A, D, and J into the original equation here? Absolutely. You get the same numbers. That might be easier. It's just not simplified. So some of them are easier. Some of them do simplify. If you recall in it might have been the previous section where we cleaned up this like surface area over volume thing, I much preferred what we did when we cleaned it up. But yeah, it just depends on the problem. Furthermore, I might like the original one more because it shows what times each individual flight was before we add them up. Anyway, I'm not complaining about the problem. I'm just stating that it's either or. It doesn't matter. Number 46, rewriting a formula. The total resistance, R sub T, of two resistors in a parallel circuit with resistances R sub 1, R sub 2 in ohms is given by the equation shown there. We probably have to simplify it. So R sub T equals 1 over R sub 1 plus 1 over R sub 2. I'll trust them. Simplify the complex fraction, then find the total resistance when R sub 1 is this and R sub 2 is that. And once again, could I substitute 2,000 and 5,600 right now into that? Yes. Could I also do it after simplification? Yes. Which one will look better? I don't know. Simplify the complex fraction here. We need a common denominator. I'm going to multiply a couple R sub 1s, a couple R sub 2s, and keep them alphabetical, alphanumeric. So there's a 1 that's just dividing by this whole thing. And if a 1 divides by something, by the way, this is R2 plus R1 over R1 times R2, then it's also multiplying by the reciprocal. The 1 really doesn't matter here, guys. I just got to flip this. This is R sub 1 times R sub 2, all divided by, and I'm going to flip these, R sub 1 plus R sub 2. I think that's the answer. So which version do I prefer? That one. It's just, it looks better. It's more plugging in, but I like it. So R sub T now is 2,000 times 5,600 over 2,000 plus 5,600. And you know what? This formula is not just for this. Doesn't this formula also work for the whole thing like Al washes a car in 2 hours, Bob washes the same car in 3 hours, how long would it take to wash together? I think this is the same kind of formula that you use, derived from the same kind of setup. And there's a reason behind it, but anyway, I believe that is the same kind of formula for that question. If they give us another problem like that, and I don't think there's a section devoted to those kinds of questions, unless it's going to involve itself in these questions here, but I don't think we have to make our own equations for it. So I'm getting 1473. I don't even know the units yet. Resistance. Resistance is in ohms, right? Where is it? 2,000. Yes, ohms. So what was my number? 1473.68. I'll say 1474. Around 1474 ohms. Okay. Okay. Number 47. And yes, I think it's that kind of question. Again, I'm not going to dive deep into it, but the whole, how long would it take to do something together if you knew your own separate things? I think this works in that same kind of way, the formula. Number 47, problem solving. You plan a trip that involves a 40-mile bus ride and a train ride. The entire trip's 140 miles. The time and hours the bus travels is here, where x is the average speed. The time and hours the train travels is here. Write and simplify a model that shows the total time of the trip. So you have a y sub 1. This is time. And y sub 2, time. You're going to add these two times. So I'll just say that y is a y sub 1 plus y sub 2. That way when I do y equals, it'll be good. So y is 40 over x plus 100 over x plus 30. As far as common denominator goes, which is the whole goal here, x plus 30 on top and bottom, x over x on top and bottom. With regard to distribution, we get 40x plus 120, and there's a plus 100x here. X times x plus 30 will be on bottom, like that. And 40x plus 100x is 140x plus 120 all over x times x plus 30. There's a common factor of 20 on top, and you get 20 times 70x plus, no, 7. I have to think about this. 120, 40 times 30 is not 120, it's 1200. It's 1200. So 7x plus, now you factor out 20, 60 all over x times x plus 30. So here's another expression for the total time simplified. And I'm not air quoting simplified as in it's not. It's just, is it simpler to you? I don't know, but it's one fraction. There's that. Did they say do anything with x? What's x based on? That's what I want to know. X is the average speed of the bus. They never simplify, they never substitute anything for x. So that's just our thing. Based on the bus's average speed, you could figure out your answer. Okay. Number 48. You participate in a sprint triathlon that involves swimming, bicycling, and running. The table shows the distances in miles and your average speed for each portion of the race. Write a model in simplified form for the total time it takes to complete the race. Okay, so time is the combination of all your things here, and time is distance over rate. So you've seen it a couple times set up for you. Now we got to kind of do our own. So time is distance over rate. So we have a couple of them. We have time for swimming. Time to float. Time for swimming is distance over rate. Time to bike is its own distance over rate. And time to run is its distance over rate. We're going to add these three times together to get our total time, but they want a simplified form of it. So part A, we have to do our total time, which is 0.5 over r. By the way, should I keep this as 0.5 or should I write it as... I'm going to get fancy with this. 0.5 over r is also 1/2, right? 1 over 2r like that. So I'm going to write 1 over 2r. I don't know if that helps or hurts, but I'm going to do it. Plus 22 over 15r. Because I don't want decimals. Listen, I don't want decimals in my fraction answer. That's a personal thing. I don't want decimals. You can have it all you want. I don't. Plus 6 over r plus 5. They're all missing something else don't got. These both share an r, but this thing's missing a 15 and an r plus 5. Let's distribute that already on top. So hold on a second. Let me split these up a little. Give me a second. I'm going to do... Otherwise, this gets really disorganized. All right, this one is missing on bottom a 15 and an r plus 5. Now, when you distribute 15 and r plus 5, you get 15r plus 75. This is missing a 2 and an r plus 5, and when you distribute that on top, you get 2r plus 10. I do that on top because I need to start cleaning up the top. This is missing 30 and r. 2 times 15 times r. It's missing 30 r, like so. Okay, now I chose to get no decimals in my answer. That's a personal preference, so I'm just going to go ahead and do with that. Same with like no leading negatives. So 1 times that is just that, so 15r plus 75. 22 times 2 is 44, so you get 44r plus 220, and then 6 plus 30r is 180r. We divide this by 2r times 15 is 30r, so 30r times r plus 5. 15r plus 44r is 59r plus 180r is 239r. So I'm getting 239r plus, and 75 plus 220 is 295. Now, there's no common factor to my knowledge. 295 doesn't divide like by 3. It divides by 5, but 239 doesn't. 239 may even be a prime number. I don't know. But, yeah, it doesn't divide by 7. Anyway, this works here. Now, if I didn't have the 1 over 2r, then this would have been half of this number, and half of that number. This would have been 119.5. This would have been 148.5. No, 147.5. And this would have been 15. But I'm going to leave it like that. That's my total time for this based on rate. Okay. Part B, how long does it take to complete the race if you can swim at an average speed of 2 miles per hour? Justify your answer. Is R, oh yeah, R is your swimming speed. So 2 miles per hour. So if R equals 2, part B, T equals 239 times 2 plus 290. Oh, that would have negated that decimal. Over 30 times 2 plus 5. Now, I want to try and do some of this in my head when I can. I don't want to make a mistake in the calculator. 2 plus 5 is 7. 7 times 2 is 14. 14 times 30 is 420. Okay. On top, I'll do that in the calculator. 239 times 2 plus 295. I'm getting 773 over 420. I think this is in hours. And 773 divided by 420 is 1.84. So I'll say what? 1.84. Is this hours? Yeah, probably hours. Total time of the whole thing. All right. Number 49. Your friend claims that the least common multiple of two numbers is always greater than each of the numbers. Is your friend correct? Justify your answer. No. My friend is incorrect. We can do this either with polynomials or with numbers, but my friend is incorrect. The least common multiple of 4 and 8, for example, is 8. Right? It's not like 32. It's not even, not even 16. It's 8, which is the same. You could do this with polynomials, and we did least common multiple of LCM. Let's even do ones with like quadratics. X squared minus 36. Don't worry, I'll clean that up. And x plus 6. That's still x squared minus 36 because x squared minus 36 is x plus 6 times x minus 6. So that's still x squared minus 36. So those are two sets of examples, polynomials, numbers, etc. And we've done both, really. Good to note, though. Number 50. How do you see it? Use the graph of the function here to determine the values of h and k. Your h is -1. Your k is -4. I have nothing more to say. We could write a whole equation. You want to write a whole equation? This is just a 1. Your a value is 1 over 1 up 1. So your whole equation, listen, that's the answer. But your equation is f of x equals 1 over x plus 1 minus 4. Just keep in mind for your equation, the h is opposite appearing, but the h value itself is -1. It's x equals. That for the vertical asymptote. Oh, that's not number 40. That is number 50. I've seen that before, by the way. When I go back and do my timestamps for my problems, I've seen that I've written a problem wrong and I never go back and correct it. I want to correct that one. Number 51. You borrow P dollars to buy a car and agree to repay the loan over T years at a monthly interest rate of I, expressed as a decimal. Your monthly payment M is given by either formula below. So I'm guessing one is a simplified version of the other. So I don't know if they're saying which one do you prefer or what. M is this or M is that. Now I prefer the one on the right side. It's not a fraction within a fraction. Show the formulas are equivalent by simplifying the first formula. Okay, so we got to simplify on our own. So I got M equals, you know what? For the sake of this, because both of them are written, let's copy and paste this one. And then I'm going to start working out the left one and show that it matches the right one after. So we begin with this guy here. Now the tricky part about this one is this is raised to the 12t power here. Is I like the imaginary number I? No, it's a monthly interest rate expressed as a decimal. I have to think about this one. Here's the problem. The problem is this exponent. This exponent upsets any sense of order of operations. When I want to get a common denominator, there's nothing. Well, okay, you know what? Never mind. Okay. here's what I can do. This is fine, actually. I was thinking too hard about the whole flipping of something. But what I can do on bottom is I can rewrite this as 1 to the 12t power over, you can do this, 1 plus I to the 12t power, which means 1 to the 12t power is just 1. So this actually can just be rewritten as 1. Now I can see my common denominator. This can be a common denominator as 1 plus I to the 12t over 1 plus I to the 12t. Okay, now I can get a common denominator now that there's something just on the bottom. I don't know how I didn't actually see that the first time. Actually, I should have looked at this a little more. Anyway, so now this is pi on top. That's p times I, by the way. That's not pi. Divided by 1. This is 1 plus I to the 12t times 1 minus 1 over a common denominator of 1 plus I to the 12t, like so. And so we get to multiply by the reciprocal. Now this is well, it's a difference of 2 squares, but I don't think we're doing that. No, we're just matching it up with what we had before. So pi times 1 plus I to the 12t over 1 plus I to the 12t minus 1. And now we can write it all as one fraction, right? This is over 1 after all. So m equals p times I times 1 plus I to the 12t over 1 times that is 1 plus I to the 12t minus 1. And I think that's the match of the original problem. I'm not going to go back up. Let's just look on the left here. pi 1 plus I to the 12t. Yes, so that's the same thing. So it's a match. We're all good to go. She's cleaned up, Captain. Nothing can cancel. We're good. Find your monthly payment when you borrow $15,500 at a monthly interest rate of 0.5% and repay the loan over 4 years. So for part B, because that was part A, for part B, and I'm going to use the simplified version, P is how much I borrow, so 15,500. Thou. I is the interest rate expressed as a decimal. Now 0.5% is not the decimal equivalent. We got to write 0.005. That's the version when you divide by 100, shift it 2 decimal places to the left. T is in years, and this is over 4 years. So with these 3 things here, we're going to solve for an m. So we have 15,500 times 0.005 over, see, I ain't in financing. I don't know if I would know this. Let me at least clean this part up here because I'm going to do it on the bottom as well. 1 plus 0.005 is 1.005 to the 12 t, and t is 4. 12 times 4, I'm going to clean that up as well. That's 48. Because I'm going to do this stuff in the calculator in a bit. All divided by 1.005 to the 48 power minus 1. Now, this is my first time seeing this formula in this way. I'm trying to make sense of some things, and I do. I make sense of some of the things. Monthly interest rate, that's why we multiply time by 12. The interest is the, addition of this thing as a decimal. I see all those things involved in my principal amount. It's there. I just don't know in full. I honestly didn't read the whole problem as far as what we repay and all that kind of stuff. So anyway, let's go to the calculator, and let's get it all done. Let's clear this out. So 15,500 times. The troublesome spot with people here is just order of operations. And because I cleaned some stuff up already, I think it'll be a little helpful in what I write. Now, when I divide, I want to put in parentheses 1.005 to the 48th power. That's fine. And then minus 1. Putting in parentheses allows both those things to work together. Then. So I'm getting this number. I got to figure out what the units are here. What is this? Find your monthly payment. So this is how much we pay monthly. So this is dollars, and I'm going to do cents. I'll do $364.02 as a monthly payment. That's not 364. $364.02. Okay. Per month. All right. It was funny. Someone earlier who worries about my finances was asking me like, "Hey, how much?" I still pay student loans. They're like, "Hey, how much do you owe on student loans every month?" I'm like, I don't know. Like, how do you not know? Don't you pay them? Yeah. How do you pay them? It's on auto pay. Do you trust them with the interest rates? Actually, now that I think of it, no. It's like when, like, you know, my internet bill jacks up, or DirecTV or whatever, or I'm still paying for Paramount Plus and I haven't watched it in, 2 years. Little things like that. I gotta get on that stuff, man. All right, 52, thought-provoking. Is it possible to write two rational functions whose sum is a quadratic function? Justify your answer. I'm sure the answer is yes. I just don't know. They mean the whole result is a quadratic. So we've seen, listen, if we go back, I want to find out how these worked, or I want to show you how they worked at least. Then I'll say like I pretended like I knew. When we go back and find... We did problems like it, so I got to find them. Give me 1 second. It was really early on. All right, so problem like this. Number 8. Number 8 was originally this, and it ended up just being a linear function. Because what happened? Things canceled on top and bottom. Things canceled on top and bottom, so it turned into a linear function from something completely different. So we want to make something a quadratic from what is a rational, which means we want to cancel something on top and bottom. But I don't want to make it so difficult that it's kind of hard to bring about. So let's make it in a very easy way. Let's do something where we are canceling an x on bottom. All right, so we'll do two what did they say? The sum. So let's add something with x on bottom. They can both be x's. And let's cancel out that x to make it so. So in canceling out the x to make it a quadratic, it needs to first be a cubic. So if I could do something like x cubed plus, I don't know, 2. Oh, well then the x's won't cancel. Let's do x cubed minus 2 and plus 2 like that. So now that becomes x cubed minus 2 plus 2 all over x, which becomes x cubed over x, which becomes x squared. So it becomes that. Sure, x can't equal 0. That's a portion of the thing with the cancellation. I get it, but it's still a quadratic. It's still a quadratic in the end, and that's what I'll deal with. All right, number 53, using tools. Use technology to rewrite the function here in that form. Describe the graph of g as a transformation of the graph of f of x. How would I use technology to make that happen? Okay, I got an idea. I just don't know if this works right. So, whoa, because we, oh, I don't write this here anyway. What we did previously was, stuff. We did it by hand. It's weird that these are not multiplied already. I don't really know what to say about that. I'm just going to rewrite the problem exactly as is. I could do this by hand, I suppose. I don't know why they have it. So, like, does this mean anything? Is this a formula? Like, why aren't these multiplied? I don't know. Why is this coefficient on the front? I don't know. My form of technology that I'm going to do is this. I'm going to type it in here. Find out where the asymptotes are. The a value is another concern. That's the thing I'm thinking about right now. The other thing, maybe they just mean use the graph, use a calculator. All right, let me see what the graph looks like first. Okay, that's no fun. Okay, maybe they're just saying use the calculator to help you. When they say use technology, I don't think they mean let it get your answer. I think they mean let it help you compute things. So we have to compute 97.6 times 0.024. And that's this number. So let me just write this to begin with. I'm going to rewrite this as g of x equals 0.003 x plus 2.3424. Whoopsie. Because I'm guessing I have no chance of doing it using the graph itself. I don't know how I'm going to get that a value without doing this myself. X plus 12.2. Okay, if you notice what I did on previous problems here, the idea is I got to multiply 0.03. I mean, listen, this will take multiple steps, but I got to multiply 0.03 with that bottom but I need to figure out how much, I need to subtract from here to make it still be the plus 2.43424 that this thing was from before. So when I distribute that out, note that I'm trying to think of how to write it. I don't want to write it in a way that confuses you, but I'm just going to write this. Okay, I'm still missing something here, right? Because I obviously changed what the nature of this problem was. I just added a whole, see, before it was just this plus this, so I still have this plus this, but now I have this in the works right here, 0.003 times 12.2. So I need to take away a 0.003 times 12.2 over here. I'm obviously going to use the calculator to help me out on that. But that's what happens through the distribution. Now I can leave that factored right there, and I can even split this up right now as I work out what this a value will be, which clearly was never going to be a very good number. What is 2.3424 minus 0.003 times 12.2? That will be my a value. Actually, this will be my a value. 2.3058. 2.3058, and this is all divided by the same x plus 12.2. So these go away. Yeah, this never would have been good on the graphing calculator to figure out what we're approaching, things like that. So now my answer is 2.3058 over x plus 12.2 plus 0.003. You know what would have made this thing better is if this was, well, if the numbers cleaned up well, but if this formula meant something. I think these are just random numbers. So I'm writing that as my equation. They say describe the graph of G as a transformation of the graph. Whoopsie. So they don't ask us to graph it, which I'm quite glad. So this is the graph of G is a translation, 12.2 units left and 0.003 units up from f of x equals, and the classic 2.3058, really glad I'm not graphing this, over x. That's a classic right there. And that's what we're translating from. Okay. All right, number 54. Find an expression for the surface area of the box. All right. How long have I gone? Yeesh. All right. The box, which I shall copy and paste the dimensions. It's not volume, it's surface area. So surface area of a rectangular prism, of any prism, is the lateral area plus the area of both of your bases. Because they're all rectangles, we can work that out a little bit. All right, so surface area is the lateral area plus the area of both your bases. Now the area of any one base, I'm going to make the bottom thing the base, is length times width, x plus 5 over x times x over x plus 1. That is, the x's cancel. Therefore, x can't equal 0. I don't know if it could have to begin with anyway. But x plus 5 over x plus 1. Okay, there's area of the base. Lateral area is perimeter of base times height. Perimeter of base times height. Perimeter of the base is 2 of these plus 2 of these. And we're multiplying this all by this. This is not a short problem, guys. So we have 2x plus 10. I still got to get a common denominator. We have 2x plus 10 over x plus 2x over x plus 1 times x plus 1 over 3. Now, in getting a common denominator, I'm wondering if I should distribute. No, I'm not going to distribute first. Let's get a common denominator with these first and then do a multiplication of. So this needs a x over x. This needs an x plus 1 over x plus 1. And 2x plus 10 times x plus 1 is 2x squared plus 2x plus 10x is plus 12x plus 10. Then this is plus another 2x squared here. And this is all over x times x plus 1. And this is multiplying with x plus 1 all over 3. Now the x plus 1s here can cancel. On the bottom you'll have 3x. On the top you have 4x squared plus 12x plus 10 And I can factor a 2 out, and you get x squared plus 6x plus 5. Oh, 3x. And then there you get, that can factor into x plus 5 times x plus 1. This is all over 3x. So this is your lateral area. So your surface area is your lateral area plus 2 of your base areas. Your base area is x plus 5 over x plus 1. So 2 of those looks like that. I hope I didn't make a mistake. Somewhere I could have, and I apologize if I did. I'll scrap it and redo it if I did. 3x over 3x here, x plus 1 over x plus 1 here. Doesn't matter that it already inherits an x plus 1. And now I actually got to clean up the top. Everything that I factored, I should unfactor again. I'm going to bring this back. 4x squared plus 12x plus 10 I got to multiply into this thing. So I'll get, you know what, I should bring that back. Hold on. This factoring didn't help. I thought I was going to multiply. I forgot I'm going to add. So let me bring those back. So this is 4x squared plus 12x plus 10, like that. And this is 2x plus 10 when you distribute the 2 with the x plus 5. So 4x squared plus 12x plus 10 times x plus 1 is 4x cubed plus 12x squared plus 10x plus 4x squared plus 12x plus 10. And then 3x times those two things are 6x squared plus 30x. And this divides all by 3x times x plus 1. So 4x cubed plus 12x squared plus 4x squared is 16x squared plus 6x squared is 22x squared. That's a 12x, right? 12x. 10x plus 12x is 22x plus 30x is 52x. Plus 10. This all divides by 3x times x plus 1. I can factor out a 2 on top. Is that it? 2, and I get 2x cubed plus 11x squared plus 26x plus 5 all over 3x times x plus 1. I don't see any factoring by grouping on the top there, so I think I'm done. X can't equal 0. What else canceled? X plus 1s, we already have an x plus 1 on bottom. X can't equal 0. Oh, sorry. There's still an x equals 0 on bottom. We already have that, so we're good. Based on their mentions. I think that's all we need. There's an expression for surface area. Okay, that's a lot. All right, let's go to number 55. Problem solving. You are hired to watch the new cars at a car dealership. I think this is the kind of questions that I brought up before. So they do bring them up here. They're just not like their own section. You are hired to watch the new cars at a car dealership with 2 other employees. You take an average of 40 minutes to wash a car. So your rate is 1/40th of a car per minute. So I'll talk about it in a second. The second employee washes a car in X minutes. The third employee washes a car in X plus 10 minutes. Write a single expression R for the combined rate of cars washed per minute by the group. Okay. Distance equals rate times time is involved here. The difference is distance is not how much you travel. It's how much of a car, washing a car. Your 1 car washed. We're going to wash 1 car in 40 minutes. An average of 40 minutes. In 40 minutes times your rate. So your rate is 1/40. That's where that comes from. That's why that is what that is. That's you. R sub 1, if you will. The second employee washes a car in X minutes. So that's 1/X. 1 car in X minutes is the rate. 1 car is the distance. And R sub 3 is 1/X plus 10. Okay. And it says, write a single expression for R for the combined rate of cars washed per minute by the group. I'm sorry. I did not mean to do that. So your total rate is your sum of your rates together. When you add them, it's like 20 miles an hour plus 40 miles an hour. You can add them to become 60 miles per hour in that way. But this is just rate. This is not time. So your combined rate is 1 over 40 plus 1 over x plus 1 over x plus 10. Now, each of these are missing what the other guy don't got. So this thing needs to get a whole 40x. This needs to get a whole 40 times x plus 10, but I'm going to go and distribute that on top to get 40x plus 400. And here, this is missing x and x plus 10, but x times x plus 10 is x squared plus 10x. So on top, we have x squared plus 10x. Oh, these are all ones anyway. Plus 40x plus 400 plus 40x. And on bottom, I'm hearing 4dx, and I'm thinking of Regal's motion seats, 4dx. 4t x times x plus 10. A lot of 40s and x's and things like that. So now that's x squared plus 90x plus 400. Does that factor? 50 plus 4, no. I don't think it's factorable. 81, no, I don't think it's factorable. Okay, so there's a combined rate. This is part A. Part B says evaluate your expression of part A. In part A, when the second employee washes a car in 35 minutes, how many cars per hour does this represent? Explain your reasoning. So for part B, if this was part A, part B is second employee washes the car in X minutes, so 35 minutes here. So we're substituting 35. So 35 squared, I'm going to let the calculator do this. 90 times 35, use technology to find out the answer. Over 40 times 35. Now there's one part I'm going to do on my own. 35 plus 10 is 45. Okay, so let's go to the calculator, and we're going to do 35 squared. Whoops. Squared plus 90 divided by, and in parentheses here, 40 times 35 times 45. Okay. Oh, that is small. I gotta think about what that number means as a whole. So this is 0, because they did say to interpret it. So if that's my number, and I trust my order of operations and my simplification, I'm getting R is about 0.0758. I'll just round to that. What is this? Cars per minute? This is this many cars per minute. That's weird. I'd rather figure out minutes per car or something like that. We don't do cars in minutes. It takes 40 minutes to wash a car, sure, but we don't say that. I'd rather do how many minutes per car or how many cars per hour. So let's do this number times 60 to figure out cars per hour. So it's around 4.55 cars per hour. That's one interpretation of this. So that's one. Sorry, I'm writing this right here. What I'm also going to do is figure out how many minutes per car. I kind of care about that a little bit more because they said 40 minutes per car before, right? So let's do a flip of that. So let's divide by 60 again, and let's raise this to the negative first power. If you don't know what that does, it takes the reciprocal. So taking the reciprocal, this is how many minutes per car we'll take together. So it's around 13.2. Around 13.2 minutes per car, which is cool, right? It's when the second guy does 35 minutes per car, I do 40 minutes per car, and the third person does 45 minutes per car. All together, we can actually come up with a number there. And like I said, that other formula thing I was talking about does apply to this, but because it's 3 people, that formula is not exactly the same as written. But all these things get some sort of answers there, and those are my different interpretations that I suppose I'd say. But yeah, that's what we figure out. All right. Those are my interpretations, at least. That's what I want to say on them. My preferred is really talking about how many minutes per car, so I can compare to our originals, or how many cars per hour. Cars per minute is just, yeah. All right, number 56, using tools, which often means calculator. The expression 2w plus 450 over w models the perimeter of the corral in section 1.1 example 3. I remember nothing about that section. Let's go with it. I'm going to pause for a second and find my video on that. Give me a second. All right, guys, I found the video and I found the portion here. So when I go to here, this is on YouTube right now. When I go here, you can see that they're talking about that guy right there. That 2w plus 450w was an example for something regarding the corral stuff. I guess we did it at the time. I sort of remember this diagram. I don't remember anything about the equation. Okay, so cool beans. Let's get rid of that. Okay, so 2w plus 450 over w. Find the sum of the terms, probably, simplify. Then use a graph to justify the value of w found in the example. Oh, I shouldn't have closed it. All right, I got to bring it back up. I just closed it. Let me go back to my history. Hold on. I lost my timestamp, though. Give me a sec. Let me find it again and pause it so we can find out what this stuff says. Okay, so they said simplify this, right? So this, you can multiply top and bottom here by w, and you get 2w squared plus 450 all over w. I can factor a 2 out if need be, and we get 2 times w squared plus 225. This is a sum of two squares, but that doesn't actually mean anything. But there is our sum of those two things together. Okay, so they said do what? Use a graph to justify the value of w found in the example. Okay, so if I have my simplified version and I go into my graphing calculator, I can do 2 times this w squared plus 225 all over w. Things like that. And graph it. I don't know what. Clearly I have to zoom out in some sort of way. Probably don't care about negatives. This is about like length and width and stuff. Let's go to like 100 and stuff like that. Figure out what this is showing me. There it is. What was the original question? Not the original question. The original in the video, in the original video here. We wanted to get these guys out of the way. We wanted to minimize the amount of fencing needed. So this was an area. Was this an area for? I'm sorry that I'm dancing around these. I haven't seen this. It models the perimeter. So we need to minimize P, which is basically our Y value, and we need to find that value that minimizes it. So going back to the graphing calculator, we're trying to find this bottom point right here, basically. So I can go to calc and minimum. Let's start from the left of it and go to the right of it. And find, enter. And our minimum is x equals, that probably should say 15. That minimizes the perimeter at 60. So W, the minimum width, min width equals 60 feet. Doesn't say the units. It doesn't say what this is feet or anything like that. So I'll just say 60. Oh, meters. Wait, is this right? I think it's meters. Minimum width is 15. 15 meters. And the minimum perimeter, not the minimum width, the width to get the minimum perimeter is 60 meters. Kind of weird example that we have to go back and forth like that. Now, as far as the video goes, the answer was, it must be 15. We have to fast forward here. You're watching an ad within an ad, folks. I did see it in a table on the calculator, though. The 15 thing. Give it a sec while this thing goes through. Gotta pay bills in its own way. All right, so right here, I see this. 15 and 60. You guys see that one right there? The 15 and the 60 are right there. And that minimizes the width. So when x is 15, y is 60. That's the min. So that confirms it, what we were talking about here before. So how is the graph different from previous graphs of rational functions? Oh, that's a good question. Okay, so first of all, this is a confirmed part. Now, I was going to mention this, but it didn't have to do with the problem. Now it does because they're asking us. How does this graph compare to different graphs? You might say, well, it's a different kind of parabola. It's not a parabola. This is a rational function. You have to remember what chapter we're in. We divided by w. If I zoom out, because I'm in a different kind of scape here, right? Let's do like negative 20 to 20. Whoops, negative 20 to 20. I think you're going to see something really unique about this graph when we get some zoom out on here. I don't know where to go though, so with my windows. Shoot, it didn't show everything else. There's something else I got to show you. I got to zoom out more, I guess. Let's go back to negative 100 and 100. Let's just zoom out in full. Negative 100 and 100. There's another side of this graph. There it is. Okay, so look at that. And we're not seeing very much of it, but you're seeing the essence of this kind of graph. This is a rational function, but it's different. In this rational function, you have axes, right? Whatever. And then you have this vertical asymptote. It's at x equals 0. That totally makes sense because of the nature of the graph thing. But it does this, and it does this. Now, what is it actually doing? You can't see it. This is hard for you to answer without you actually knowing and seeing the entire graph. But we have this vertical asymptote. We don't have a horizontal asymptote. We have something called a slant asymptote. So how's this graph different from our other ones? It doesn't have a horizontal asymptote. It has an asymptote that does something like this. You can't see it on the actual graph itself, but that's what this one is doing. So this graph, this is something you just got to hear me with the answer on. This graph has a slant asymptote instead of a horizontal asymptote. Now, if you want to know more about that, I have some other graph videos that do talk about it. The reason is because this is a w squared and this is w to the first power. They are not equal degree, and the denominator is not a larger degree. The numerator is 1 degree larger. That makes this have a linear function quotient. If we did long division, you might see more about it, but that's all I'm going to get on there. All right, number 57. The amount A in milligrams of aspirin in a person's bloodstream can be modeled by what you see there. It's good to know for myself, I guess. Sorry, I have to write it. Probably should have copied pasted it. How do they figure this stuff out? Where t is the time in hours after one dose is taken. There's a combined effect. The amount can be modeled by this. T is the time after one dose is taken. A second dose is taken 1 hour after the first dose. Write an equation to model the amount of the second dose in the bloodstream. So with the second dose, T is the number of hours. 1 hour later, you got to do T minus 1. Right? The right shift, this right shift is a T minus 1, if you kind of understand how that thing works. So for part A, I guess you just substitute T minus 1 into here. So 391 times, I don't think they're asking you to simplify. T minus 1 squared plus 0.112 over. But we might have to add these. 218 T minus 1 to the fourth plus 0.991 times T minus 1 squared plus 1. Okay, that to me is your part A question about 1 hour later. Because you got to plug in 1 for T to get the same Y value as you would when you plug in 0 for T here. Things like that. Part B, write a model for the total amount of aspirin in the bloodstream after the second dose is taken. There's no way they're going to ask us to simplify this. So I'm just going to write these as two combined things. Like just this plus that. So honestly, for me, it's going to be a copy-paste job. Now that I wrote it once, I think I'm good. So these two things together, there's absolutely no way they are going to force you to combine like terms on that. I know they've had wonky problems before. There is no way that they're going to say, hold on, I have to copy and paste this. They're going to say, get some common denominator. Schlug. Oh no, hold on a second. I run out of room. Give me a second. I'm trying to fit everything and I can't. I just can't do it. Okay. I have to put a plus in between these. No, I lost my +1. I can't do it. That would have been a lot easier to just rewrite it again. I apologize for doing all that. All right, I think it's just this plus this, y'all. I don't know. Oh, this squared. I don't know what else I can really get done with that other than write those two things together. That's the combination. And they're not asking anything else about it, but they gave me some scientifically accurate information, I suppose. Okay, so that's number 57. I think that's it. Number 58, finding a pattern. Find the next two expressions. Find the next two expressions in the pattern shown, then simplify all 5 expressions. What do the expressions approach? Are you serious? Well, I'm going to copy and paste that to begin with, just so we can figure out the rest of the pattern from there. So this one begins... Find the next two expressions. So this the first, that's the second, that's the third. The fourth, there's clearly a 1 plus, and it's 1 over something. So what you can see here is we front a 2, and then first it was 1 over 2. Now it's 1 over 2 plus 1 over 2. So it's a repeat of 1 over 2, but you add a 1/2 to the 1 over 2. I don't know if I'm saying that right, but I need to make sure that I have the right number of these here. This one is here, so we've got to do 1 over... I guess we just got to do 1 over this. We just got to do 1 over this, right? So 2 plus 1 over 2 plus 1 over 2 plus 1/2. I think that's one more than this one, right? Because that's all these together, so 2 plus all that. Let me make sure I did one more than they had. 1, 2, 3 2s, and 1, 2, 3, 4 2s. Yes, the 2's got a little smaller, I apologize. That's the 4th term. The 5th term is this same thing, but... Let's see if I can fit this. Give me a second. I am going to copy and paste that. So it's the same thing, but this has... I think instead of... There's still a 1 over this. There's a 1 plus here, and there's 1 over this whole thing, but this one needs to turn into a 2. So if I am doing that right, there's 1, 2, 3, 4, 5 2s there, 1, 2, 3, 4 2s there, 3 2s, 2 2s, 1 2, followed by the 1 that's up there. Now they stated, what value do the expressions approach? I guess if you're getting... I don't know if I need to plug them all in or what. But I guess here we're doing... I'm trying to think of a way to clean this up so I don't have to do so much work on this as an overall. Let's do 1 over 2 plus 1/2. And then I'm going to do... Oh yeah, that's 1 over 2.5. So that number plus 1 is 1.4. So that's the first number in this set. The second number, I don't know how to do this quickly, so I'm just going to have to work this out. 1 plus 1 over 2 plus 1 over 2 plus 1/2. And I don't need closing parentheses. I know what I'm doing in the calculator, so I'm good on that. So there's that number. That is, okay, I can probably do this. I can probably insert in front a 1 plus division parentheses and change this into a 2. I think that'll do that. Nope, I messed something up. Oh, that shouldn't be, this is just 1 over, not 1 plus. Wait, yes, 1 plus 1 over that. Okay, let's see if that works. Okay, now what is it approaching? It's at 1.4. Is it going down or is it going up? I can't tell. This one, I'll do the same thing, but I need to turn this into... Is that the 3rd term? I don't know what term I'm on anymore. That's the only problem. 1 plus 1 over, and then I turn this into a 2. So I have the next set. Oh, I need parentheses. And then that is that, no, okay. I might have messed up on the one before, but this at least is going up through this approach. And then this one, I think that was the fourth term. Let's do one more. 1 plus 1 over parentheses and turn that one into a 2. 1.41420. Maybe they are changing. Maybe they are going higher than lower than higher than lower. I think it did up, down, up, down. So far, it's approaching 1.414201183. I don't see if there's a repeat of numbers. Is it 414141? You know what this might be close to? It might be close to the square root of 2. I know the square root of 2 is 1.4 something. Square root of 2 is... Oh, that has to be what it's approaching. Okay, let me do this really fast. I'm going to do this at least 2 more times and see if it gets a little closer. 1 plus 1 over parentheses and then turn that into a 2. And then one more time. 1 plus 1 over parentheses and turn that one into a 2. Let's see how close it gets to that square root of 2 number. Oh yeah, this is approaching the square root of 2. For sure, for sure. Okay. So that's approaching square root of 2. So there's clearly something in terms of how we can use that fraction to approximate square root of 2. I don't know why, personally. I think I used to know how that stuff works, but I had no idea from here. But that's what it kind of looks like, and that's good enough for me. If that's good enough for me, it's good enough for, hopefully for you. Because, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Kind of a deep section in the end with the kinds of word problems that we had, which was interesting because the lecture didn't actually do any word problems with those. We had to manufacture those ones on our own. The graph stuff got a little weird, and what was unfortunate to me was they never did problems like the lecture one where they combined like terms on the top and factored and canceled out with something on the bottom. Those are my preferred ones to do. Hopefully within the review or chapter test we get something like those. Section 6 point, I don't know what section we're on, 6.4? Section 6.5, the final section in this one is going to be solving rational equations. So take everything that you learned from the past 2 sections and we're going to use them there. Thank you guys so much. Big lawnmower. Take care. I'm going to see you in the next one.